Hello and welcome to the following lesson on Introduction to Radioactivity, which is part of the nuclear physics topic in AQA A-level physics. So in today's lesson we're going to introduce ourselves to radioactivity by looking at understanding the properties of radioactive emissions. So if we've been successful and learned in today's lesson, we should be able to understand why radioactivity occurs in nuclei, understand the different compositions of the types of radioactive emissions, and then understand the different properties of the different types of radioactive emissions, which links into the following part of the AQA A-level physics specification 3.8.1.2 alpha, beta and gamma radiation. So in France, scientist Henri Becquerel in 1881 realized that the element uranium was emitting energy in the form of particles. Now this seemed to break the laws of energy conservation known at the time, because we know that energy can't be created or destroyed, and it was seeming that uranium was creating energy in the form of particles from nothing. However, this was solved when it was realized the energy was coming from the unstable nuclei of the uranium itself radioactively decaying and releasing nuclear radiation. So with this, Becquerel had discovered radiation and radioactivity. So this solved where the energy was coming from, but what in fact is nuclear radiation? What causes nuclear radiation to occur, and why do only some nuclei exhibit radioactive behavior? So nuclear radioactivity is the process of a nucleus becoming more stable in its configuration. So there are three types of radiation. There is alpha, beta and gamma radiation, which when the nucleus emits can turn from an unstable nucleus into a more stable nucleus. So you can have either alpha, beta or gamma. Now why does each process increase the stability of the nuclei? So to understand which nuclei are unstable and wish to emit alpha, beta and gamma radiation, we've got to consider the nuclear stability curve, because this curve allows us to observe which processes increase the stability in different isotopes. So it looks at the relationship between the proton number and neutron number in the stability of a nucleus. So the stable and nearly stable atomic nuclei as a function of protons against neutrons shows the following idea: that actually, for stable nuclei, the number of protons has to equal the number of neutrons. But for large stable nuclei, the number of neutrons has to be greater than the number of protons. Now, why is this the case? Now, we can explain this trend by considering the forces inside a nucleus, which consist of mainly the attractive strong force and the repulsive electromagnetic force. So if the strong and electromagnetic force are approximately equal in size, the nucleus is unstable, so it will make it susceptible to radioactive decay, whilst if the strong force is much greater than the electromagnetic force, the nucleus is very stable and the nucleus will not decay, whilst if electromagnetism was greater than the strong force, well then the nucleus would never even form, because the repulsive force will be greater than the attractive force. So it's important to note that this tells us why some nuclei form in the universe and why other nuclei are unstable. So firstly, for small nuclei, why do you get to the idea that the strong force is much larger than the electromagnetic force when the number of neutrons equals the number of protons? Well, it's because both the neutrons and the protons will experience the strong interaction, and the strong interaction is just greater than the electromagnetic interaction, so when they're equal in number, the strong force is much larger than the electromagnetic force. But for large nuclei, we have an issue. The nuclear radius has now become so large that the size of the strong interaction has decreased, since the range of the strong interaction is now smaller than the nucleus itself. So to increase our strong interaction, to make it show it is now greater than the electromagnetic interaction, you need to have a greater number of neutrons in the nucleus than there are protons to compensate for this short range of the strong interaction, because the neutrons will exhibit the strong interaction and mediate that without the repulsive electromagnetic interaction, whilst the protons will do both. So adding more protons will not have much of a difference to this. So it's very important to know this. But please remember, this can only be done for a certain amount of neutrons. Eventually, if the diameter of the nucleus is much larger than the strong force range, there'll still not be enough strong force produced across the nucleus to make it larger than the electromagnetic force. So this means that the size of the nucleus can only be approximately the size of the strong force interaction range, which is why the nucleus is so small in the atom. Because eventually, if the nucleus would increase in size so much that the electromagnetic force would be the dominant force still, due to the short range of the strong force. So to increase the stability of the nucleus, we've got to decrease the nuclear diameter at that point. So to become stable again, the nucleus must decrease in size, which you can do by emitting an alpha particle. And again, if a nucleus has too many protons compared to neutrons, it's unstable, since that will allow the electromagnetic force to be larger than the strong force due to the lack of neutrons providing the strong interaction without that electromagnetic repulsion. So you must decrease the electromagnetic repulsion, yet keep the strong attraction the same. So to do this, you can increase the stability, which happens with the nucleus turning a proton into a neutron, which is beta plus emission. And then finally, if a nucleus has too many neutrons compared to protons, it's unstable. This instability comes from quantum fluctuations due to the increased quantum states of having a large number of neutrons. It's postulated that the increased number of neutrons can cause quantum fluctuations, which can trigger nuclear decay. So in this instance, to increase stability, the nucleus turns a neutron into a proton, which is beta minus emission. So in nuclear decay, the nuclei change from unstable nuclei into more stable nuclei, which increases nuclear stability. Now, most processes by which this takes place is the weak interaction. So a W boson is passed from the unstable nuclei to the stable products. So the decay process lessens the impact of the electromagnetic force and increases the strong interaction by decreasing the nuclear radius. Now, the only exception to this is alpha decay, because it doesn't involve leptons or quarks changing type, so it decays by the strong interaction. So the alpha decay is a very, very fast interaction. Now, a decay process can be thought of as a snowfield on a mountain. So on a snowfield, whilst the friction between the ice crystals may be supporting the snow's weight, the system is inherently unstable and wants to go to a state of lower potential energy, which is the concept of entropy. Objects tend to states of lower entropy. So to do this, the snow has to crumble, relax and release energy. So a disturbance will facilitate this path to a state of greater entropy. And again, this is very, very similar to an unstable nucleus, which is unstable because the electromagnetic and strong interactions are equal to each other. So an unstable nucleus will move towards the ground state, a stable state, and radioactively decay products such as energy or particles, and the total energy will be distributed over a larger number of quantum states. So the stability is increased as the energy is spread out over more quantum states, decreasing the entropy of the nucleus. So like an avalanche going down a mountain hill, avalanches observed in one direction towards the ground state, the state with the largest number of ways in which the available energy could be distributed, which is the same as a radioactive nuclear decay. Without placing work into the system, energy always spreads out over more quantum states. Now, radioactive decay needs this activation to start it, like a spark causing a fire. Now, for a snow avalanche, the energy comes from a disturbance, like a noise or a movement, and in the case of an excited atomic nucleus, the arbitrarily small disturbance comes from the interaction of the forces in the nucleus and the exchange of a boson. Now, the similar sizes of the electromagnetic and strong interaction in the nucleus means a small disturbance can cause a decay. So in certain cases, actually random quantum fluctuations are theorized to promote the nucleus to relax into an energy state, which is the decay, in what we call quantum tunneling. So let's just clarify what we know by radioactive decay. Nuclear radiation is emitted by an unstable atomic nuclei to become more stable. Now, nuclear radiation is ionizing radiation because it can produce ions by knocking electrons out of the atoms it collides with. So an unstable nucleus can decay by emitting either an alpha particle, beta particle, gamma ray or neutron. Now, the different types of radiation can be identified experimentally using their properties. Penetrating power or absorption by different materials can be measured. Now, penetrating power is used in industry to control the thickness of sheets of aluminium foil, paper and steel. So let's consider alpha, beta and gamma emissions, and let's see what their different properties are. So the first one to consider is alpha radiation. Alpha radiation is the release of an alpha particle and occurs in large elements like uranium and radium. So an alpha particle is 2 protons and 2 neutrons, and the alpha particle doesn't travel very far, so the best way to protect yourself from alpha radiation is to keep about a meter away or use clothing or a face mask. Now again, this process occurs due to the strong interaction, and it happens with the exchange exchange of a gluon. Now let's have a summary of alpha radiation. So it's important that alpha particles will deflect in electromagnetic fields, and alpha particles produce 10 to the 4 ions in every millimeter it travels, which is the most ionizing type of radiation. Now alpha particles are just helium nuclei. Now it's important that helium is safe whilst alpha is dangerous, as the alpha has no electrons, which means it will ionize electrons from other atoms, and it will travel much faster than normal atoms. So that's why alpha is dangerous. Now it's important to know, as we said before, alpha radiation, as it's positively charged, is deflected in electrical and magnetic fields towards the negative and south pole. Now a beta particle is emitted when a neutron in the nucleus changes into a proton, releasing a negative charge in the form of a fast moving electron. Now again, this process occurs due to the weak interaction, as it involves leptons and a quark change, so this happens due to the exchange of a W boson. Now beta particles again have a specific charge, the high specific charge of any of the radioactive emissions, and beta particles produce 10 to the 2 ions in every millimeter they travel. Now a beta particle is different from a regular electron because a regular electron exists in energy levels around the nucleus, whilst a beta particle originates from the nucleus. Now beta radiation, as it's negatively charged, is deflected in electrical and magnetic fields towards the positive or north pole. Now like mentioned before, this deflection is greater than alpha radiation, as the beta particle has a high specific charge divided by mass, than the alpha particle. Now, after a nucleus has emitted either an alpha or a beta particle, it can have too much energy. So we say it's in an excited state. So it tends to get rid of this energy by emitting a very high frequency photon called a gamma ray to go back to ground state. Now, gamma rays have no mass and no charge, but gamma radiation is very penetrating and has a long range. So you need to protect yourself with at least 10 centimeters of lead or be quite a long distance away from a gamma source. So gamma radiation has no specific charge, and it produces 10 to the 1 ions in every millimeter it travels. Now gamma radiation is fundamentally no different from light, but gamma is more dangerous than light as it has a higher frequency, so it carries more energy per second and therefore has a greater ability to ionize. Now gamma radiation, as it has no charge, is not deflected in either electrical or magnetic fields. So this ionizing radiation is dangerous because ionization can damage the atoms of molecules in living cells. High doses of ionizing radiation can kill living cells, and even low doses can cause cell mutation and cancerous growths. The ionizing effects of alpha, beta and gamma radiation are different, so have different health risks associated with them. Alpha radiation is dangerous inside the body as it affects all the surrounding tissues, but outside the body it only affects cells in the skin and the eyes, whilst beta radiation are dangerous inside and outside the body as they can reach cells throughout the body. Now we can examine the properties of radioactivity using radioactive sources. These tend to be kept in lead-lined boxes to prevent alpha and beta leaving the box and reducing the amount of gamma radiation leaving the box. Now the lead itself does not become radioactive, it will just block the radiation. Now the sources themselves should always be handled with tongs. Now this prevents your hands from becoming contaminated. Now contamination is the process of an unstable nuclei coating an object. This is different from irradiation, as that's the process of the ionizing radiation passing through the object. Now contamination is a lot more dangerous than irradiation because contamination leads to long-term irradiation and the distance factor in nuclear radiation is removed. Now the sources should always be placed in secure handle, never touched by your hands. So this prevents your hands from becoming contaminated. Now you would always place a source in a holder found in a clamp stand, but it's important that this holder will become contaminated after use. Now when working with ionizing radiation, people must always take precautions to protect against irradiation and contamination. Now this includes keeping as far away as possible from the radiation source, spending as little time as possible in the presence of the radiation source, and shielding yourself from the radiation using either concrete barriers or lead plates. Now you can measure how many radioactive particles, alpha, beta or gamma, hit a tube with a Geiger-Müller counter. Now this can't tell us the difference between the different types of radiation, but we can use it to measure the count of a radioactive radioactive source. Now, before you take any measurement, you should always measure the background count. Now, any radioactive reading must have the background removed from its value, which we call the corrected reading. So that's just the amount of radioactive emissions in the background of the actual area you are in. So there are many different sources of background radiation. These include the air, because radioactive radon rocks, gas is released from rocks, which is normally the largest part of background radiation on the Earth. You've got grounds and buildings, because nearly all rocks on Earth contain radioactive materials. You've got cosmic radiation. Cosmic rays are particles from space. When they collide with the particles in the upper atmosphere, they produce nuclear radiation. Living things is a source of background radiation, because all plants and animals contain carbon, and some of this will be radioactive carbon-14. And finally, artificial radiation. Radiation made by humans from either medical or industrial sources. Now, there is always a background reading in every measurement taken. So you've always got to consider the effect of the background radiation reading. Now, the longer you take your reading, the lower the percentage uncertainty of the background. This occurs because radioactive decay is a random effect and has to be treated differently when calculating percentage uncertainty. In addition, you've got to take multiple measurements for the background count and then take an average value. Be aware there can be no anomalous values, as radioactive decay is a random process. So a Geiger-Müller counter can be used to test the effect of air on the radiation, which we call the range of radiation. So in these investigations, you move the Geiger-Müller counter away from the radioactive source until no discernible reading can be taken by the device. You can also use the Geiger-Müller counter to test the effect of objects on the radiation, which we call the penetration of the radiation. So in these investigations, you place the counter on and the source on either side of an object and see if you get a measurable value on the counter. Again, you can also look at how the radioactive emission is affected in electromagnetic fields. So it's important to note that even beta particles will follow Fleming's left-hand rule in a magnetic field, and you can work out the direction they will move in. This is a synoptic link to both magnetic fields and specific charge, which is found in other parts of the course. Now, the nature of gamma radiation leads to an important property when carrying out nuclear experiments. Gamma radiation is never completely absorbed, unlike alpha and beta. It just gets weaker and weaker and weaker until it can't be distinguished from the background. So this is a very important principle in physics called the inverse square law, which we'll look at in upcoming lessons. So it's important to note that it can never truly disappear from your readings. It will only get smaller and smaller until it can't be distinguished from the background count. So you'll notice in these particular sets of experimental results, the gamma rays will have been absorbed at approximately 4 meters, since the radiation count is now the same as the background count approximately. So therefore we can say that therefore there must be no alpha, beta or gamma radiation coming from that object. So what have we learnt in today's lesson? We should hopefully understand the properties of radiation and experimental identification of using simple absorption experiments, and also the relative hazardous exposure to humans, applications to include thickness measurements of aluminium, foil, paper and steel, applications to include the safe handling of radioactive sources, and what the background radiation is, examples of its origins, and experimental elimination from calculations. So if we've been successful in today's lesson, you should be able to understand why radioactive activity occurs in nuclei, understand the different composition types of radioactive emissions, and understand the different properties of the different types of radioactive emissions. So I hope you've enjoyed today's lesson on radioactivity and an introduction to radiation. Thank you very much for listening and have a lovely day. Hello and welcome to this lesson on the inverse square law, which is part of the nuclear physics topic in AQA A-level physics. So in today's lesson on the inverse square law, we're going to look at describing the inverse square law. So if we've been successful and we've learned in today's lesson, we should be able to understand the different properties of gamma ray emissions, describe and define the inverse square law process, and calculate values of radioactive intensity due to the inverse square law. Now, this means in today's lesson, we're going to be covering the following part of the AQA A-level physics specification, 3.8.1.2 alpha, beta and gamma radiation. So to understand about nuclear decay, the first thing you're going to consider is in fact a light bulb, because if you want to consider how light bulbs radiate energy, you've got to consider the particle model. So the light bulb will emit photons of visible light, and the energy of each photon is given by the equation energy is equal to hf, Planck's constant, times by the frequency of the photon. Now, fundamentally, you've got to consider how is this different to a radioactive source emitting gamma radiation? Well, the difference is the photon emitted by the light bulb is a visible light photon, and the photon emitted by a radioactive source is a gamma photon, which is a photon with a greater frequency and therefore greater energy than the visible photon. But apart from this, the process is actually identical. So you can consider a gamma source is just emitting photons of gamma radiation from its surface. Now, if you consider a light bulb, what happens to the light as you move away from it, and why is this? Well, as you move away from the light bulb, there's a greater area for the photons to travel in. So this means that the photons spread out, and we observe this as a human by the light bulb looking dimmer. So we say that the light source has gotten less intense. So it's a very, very important idea to consider. So what happens now when you've got a gamma source? Well, as you move away from a radioactive gamma source, there's a greater area for the photons to travel in. So this means that the gamma photons will spread out, and we observe this with a Geiger-Müller counter. So we say that the radioactive source has gotten less intense. So this indicates to us that the intensity of the radioactive source will change with distance, because we'll note that the photons are closer together near the source, whilst the photons are further apart the further away you get from the source. So you've got a greater intensity of the photons near the actual the source emitting the radiation, and you've got a lower intensity the further away you travel. So you can see this in the following diagram. So for a light source, the light source gets dimmer when you move further away from it, because there's a greater area for the photons to cover, so the photons spread out. So we say the light has become less intense. So in a similar situation, for a radioactive source, the radioactive source gets less intense when you move further away from it. That's because there's a greater area for the photons to cover, so the photons spread out. So we say the gamma radiation has become less intense. So it means that because the photons are closer together, the closer you are to a source, and the photons are further apart, the further you are away from a source, that a gamma source becomes less harmful if you move further away from it. So this relationship is only shown with gamma emissions because alpha and beta emissions are ionized by the air very quickly and don't travel far enough for this effect to be observed. So we can see it in the following image here. So you can see that as you move further and further away from the source, that the intensity will decrease because the area in which the photons can travel in has gotten much larger. Now, as the area spreads out with the square of a radius, since it is a sphere, because the radiation is emitted in a sphere situation, the relationship is not a proportional one, rather it's an inverse square. So you can observe this with the following idea. If you consider a gamma source, well, it will emit photons in every single direction, so it will form a sphere of photons around it, and the further away you get from the source, the larger the sphere becomes, so therefore the photons can spread out more. So if you took readings of the intensity of the radiation, it'll decrease by the square for the distance from the source. That's because the surface area of the sphere of photon emission is 4 pi r squared, so it goes down by a factor of r squared. So as such, an inverse square law relationship is represented on a graph via an exponential decay curve such as the following. Now this is actually similar to the discharge curve of a capacitor covered on another topic in this course. Now the value on the y-intercept is the intensity of the source, and the graph line never meets the x-axis as the activity of gamma radiation never reaches zero. So in today's lesson we're going to consider this inverse square law of gamma radiation. So let's just summarize what we've learned so far. Gamma radiation emitted from a source will spread out. The gamma radiation from a small source can be considered the same in all directions. It's isotropic, so you can therefore imagine a sphere around the source. As you move further away from the source, the bigger the sphere gets, So the same amount of energy, the same amount of photons is shared over a greater surface area. So the further we move away from the source, the less the intensity of gamma radiation. Now the intensity I of a source is the radiation energy passing through a unit area per second, and we denote the intensity at the source of the object as I0. So like we said before, the intensity decreases by a factor of 1 over the square of the distance from the source. So for example, doubling the distance from the source decreases the intensity by a factor of 4. Increasing the distance from the source by a factor of 3 will decrease the intensity by a factor of 9. So therefore the intensity varies with the distance from the radioactive source according to the inverse square law. So intensity therefore could be considered as power over area. So for a point source emitting n gamma photons per second, the energy of each photon, E equals hf, where f is the frequency and h is the Planck constant, which is derived from photon theory. So if there are n photons emitted per second, the total energy emitted every single second is nhf. So the radiation emitted from the point source is emitted in all directions, so the distance r from a source that passes through an area of 4 pi r squared, the surface area of the sphere of photon emission. Now we've just defined intensity as the power, which is the energy per second, divided by the area. So we can now substitute these values in which we've just derived. So we can say intensity is equal to nhf, the energy emitted per second, divided by the surface area, 4 pi r squared. So now we can simplify this to I equals k over r squared, where k is equal to nhf over 4 pi. This can happen because n, h, f, 4 and pi in this situation are all constant values for the same radioactive source. So this means that k is a constant for all distances from the source. So this means that it can be used to solve problems on gamma emission. Now obviously you'll have worked out that we're assuming that there's a constant activity from the source as it's taking place. So here is the graphical link between the distance from the radioactive gamma source and the activity of the radioactive source. So in gamma emission sources, there's a major fall-off of activity from when you move slightly away from the source, and the fall-off effect lessens the further you are away from the source. So this is the intensity of the radioactive emission of the source at the y-intercept, which is referred to I0, and like we said before, the intensity of radioactive gamma emission never reaches 0. So this shows us that the intensity of the radioactive source at different distances can be expressed as in terms of the intensity at the source. So it can go from I0 to I0 over 4, I0 over 9, so on, so on, so on. Now, therefore, we can say that the intensity at different distances from a radioactive source is I is equal to I0k over r squared. Well, like we said before, the intensity of the gamma radiation at the source is I0. This is used because it can account for the activity of the radioactive material as well as the spreading out of the photons in the surroundings. So the higher the natural radioactive decay of the material, the higher the value of I0, the higher the radioactive intensity measured. But remember, we can say that because I0 is a constant, k is a constant, that therefore intensity I is proportional to 1 over r squared. So this gives us our inverse square relationship. So what we can say is a point source of gamma rays emitted in all directions about the same source will follow the inverse square law, because the intensity of gamma rays decreases with distance from the source because the rays are spread out over a greater area as the distance increases. So in this relationship, we assume the gamma source has been placed in a vacuum, so it isn't being ionized by the air, that the gamma source emits isotropically, it's the same in all directions, and we're also assuming there's no background radiation contributing to this intensity value. So we can therefore write it as I is equal to ki0 over x squared. Now in the previous derivation we just said x was r. Now remember, I0 is the intensity at the source and k is a constant. So intensity is measured in watts per meter squared. Now, just be careful that in the equation booklet you're given in your examination, the term is denoted as x and not as r. So it's very important we understand that x is the distance between the radioactive source and the Geiger counter. But we don't always need to know the intensity at the source to find it at a given distance. So if you consider 2 points, A and B, a certain distance away from the same gamma source, we can write out our equations for the intensity at point A and the intensity at point B, and at this point we can actually equate the intensity I0 of the two radioactive sources, because we can cancel out the intensity of the source on those calculations. Now this can be done because the 2 points are measured from the same source, so then I0 is the same for both of the points. So we can combine them as follows. So we can say IAXA squared is equal to KI0, which is equal to IB XB squared, because they've both got the same value of K and of I0. So therefore we can equal them to each other, and therefore you can find certain values. Now this format of the equation is not given in your examination book, so you've got to be able to deduce this for yourself. Now previously we also stated that we hadn't considered the background radiation reading for your gamma ray source, but you can also do that in your equation by considering C, which is the count due to the background radiation. So at this point you can also add this factor of C in the equation as shown in the following equation. I is equal to K I0 over X plus C squared, and we call this value of the intensity the corrected intensity, because we've now corrected it for our background radiation. So let's now look at an example of a calculation involving the inverse square law. So let's consider that if the intensity of the radiation 0.5 meters from a gamma source was measured as 2.5 times 10 to the minus 10 watts per meter squared, what would the intensity be measured 1.5 meters from the source? So the first step you do is, with the information given, you can find out the value of K, which is the constant in the equation. So when the intensity, K, is 0.5 meters away from the gamma source, it is actually 2.5 times 10 to the minus 10. So we can say I is equal to K over X squared, and therefore use that to work out K when the intensities when measured from 0.5 meters. So we do that and we find that K is 6.25 times 10 to the minus 11. Now the second step links to the following part, that this is a constant in the gamma source emission, so we can now use K in our equation to find the intensity at 1.50 meters. So we can now say I is equal to K over X squared. We know what K is because it's just the value you calculated previously, 6.25 times 10 to the minus 11. You divide it then by 0.50 squared to get your answer to be 2.8 times 10 to the minus 11 watts per meter squared. Now this value makes sense, as the intensity at 1.50 meters is much lower than at 0.50 meters, as the photons are spread out over a greater area. So what have we learned in today's lesson? That the inverse square law for gamma radiation is I is equal to K over X squared, and we know experimental verification of the inverse square law. So if we've been successful and learned in today's lesson to be able to understand the different properties of gamma ray emissions, describe and define the inverse square law process, and calculate values of radioactive intensity due to the inverse square law. So I hope you've enjoyed today's lesson on the inverse square law, which is part of the nuclear physics topic in AQA A-level physics. Thank you very much for listening, and as always, have a lovely day. Hello and welcome to the following lesson on the inverse square law investigation, which is part of the AQA A-level nuclear physics topic. So in today's lesson we're going to look at detailing the inverse square law experimentally. So if we've been successful and learned today, we should be able to explain why gamma radiation follows an inverse square law relationship, carry out an experiment to verify the inverse square law relationship, and finally experimentally verify the inverse square law relationship for gamma radiation, which links into the following part of the AQA A-level physics specification, 3.8.1.2 alpha, beta and gamma radiation. So in the following investigation you're going to determine and prove the inverse square law for gamma radiation. So the apparatus you would need would be a gamma source, for example cobalt 60, tongs, a source holder, a clamp stand, a boss, a clamp, a Geiger Muller tube suitable for gamma detection, a scaler, a stop clock and a meter ruler. So to carry out this investigation you would set up a Geiger Muller tube or counter with a scaler in a classroom. You would then take a background count for a particular time and determine the background activity of the room. Now again, you must decide this time over which you take your background count. You then place a radioactive source of gamma radiation securely in a clamp stand. Then using a ruler you place the Geiger Muller tube a distance away from the source. Again, you must decide the distance you you place it away from the source. You would then turn on the scaler and with the aid of a stopwatch determine the count rate of the radioactive emissions from the source for a particular time. You then repeat this procedure for a number of times that you decide. You would then determine the mean count rate and the activity of the source. You would then calculate the corrected activity by subtracting the background activity from your measured activity of the source. You would then repeat the experiment for different distances from your radioactive source, but once again you must determine these distances. So let's just have a look at what you've got to carry out. The first thing you would need to do is set up a scaler with a Geiger-Müller tube in a classroom. Now a scaler and Geiger-Müller tube is a measuring device which counts the numbers of radioactive particles or emissions present in an area. Then the first thing you would do is record the background count for a particular time. You can then calculate your activity or count rate from this. So when the background count is taken, the radioactive source should not be in the area. This is done before the radioactive source is in the room, as the radioactive source might contaminate an area. It's always extremely important you take your background count before the source is placed in the room. Now you can calculate your activity or count rate by doing the equation of the count divided by the time. So you must decide the time taken for your background count, but what we tend to find is the longer the background count is measured for, the more reliable the result. Once this is done, you would get a clamp with a clamp stand. You would then place the Geiger-Müller tube with the ruler directly underneath it to measure the distance. So it's very important you ensure the detector is aligned with the start of the measuring scale on the ruler, otherwise you would get a zero error on your results. You would then retrieve the sources and they're kept in a secure box. Now this box should be lead lined to prevent excess irradiation. Now inside the boxes the sources are protected by lead. Now the lead here is what we call irradiated, not contaminated, because the radiation is only passing through the lead, it's not having the nuclei actually coating the lead. You would then set up a clamp stand to secure the radioactive sources. Now when you're handling the sources, only ever handle them with tongs, because using tongs prevents contamination of the unstable nuclei from that particular radioactive source coating you or your clothes that you are wearing. You would then remove the secure lead casing. Now again, the lead is completely safe to handle because it's not being contaminated, only irradiated. Then using the tongs, you would handle the radioactive source with care, and you'd place the source in a secure holder as shown in this particular diagram. You'd then attach it to the clamp stand as shown here. You'd then securely secure your radioactive source in the clamp stand, and the gamma source is then rotated to face your Geiger-Müller counter. You then place the source in line with the Geiger-Müller tube or counter, so they've got to be directly aligned with each other, again ensuring that your Geiger-Müller tube and your radioactive source are both directly underneath the measuring scale of the ruler. So you then position your source and the detector a set distance away from each other. Once again, you must choose this particular distance. Then using a stopwatch, you would measure the count rate with the detector for a set time. You would then repeat this a number of times, calculate a mean, and then determine the activity by dividing your count by the time taken. Now in theory, the repeat should be taken for each value on order of 10 to the 2 times to reduce the random effect of the radioactive decay. But obviously in the time taken for a lesson, you don't have time to do this, so you've got to decide the time taken for the count rate and the number of repeats that you would take. Now to take a measurement on the scaler, you would flip the switch on the device, which will freeze the reading. Now this will increase the accuracy of your results, as it will allow you to take the count at a particular time. You then record your results and then reset the device before use again. Now you then repeat the investigation for a set number of distances. Now remember, you must calculate the corrected activity for your radioactive source by subtracting the background activity from your measured activity. Please remember to have the gamma emitter in line with the Geiger-Müller counter. Now when you're deciding the number of distances that you need to take your measurements for, you must decide the values and the number of distances you wish to take. Now a couple of things: ensure you are always faced away from the source and are never directly facing it. This improves the safety of the investigation as it reduces excess irradiation. And then ensure that you put the radioactive source away immediately after you finish taking the readings to once again reduce the excess irradiation. Once you've got your experimental results, you would draw a graph of these results. You place the corrected activity on the y-axis and the distance between the source and the detector on the x-axis, and and you will get a graph which looks something like this. So you should see that as the distance doubled, the corrected count rate will drop to a quarter of its value, so it supports the inverse square law of gamma radiation. So to summarize what we've learned in today's lesson, that the inverse square law for gamma radiation is equal to I is equal to K over X squared, and we've looked at the experimental verification of the inverse square law, including an investigation of the inverse square law for gamma radiation. So, if we've been successful and learned in today's lesson, we can explain why gamma radiation follows an inverse square relationship. We can carry out an experiment to verify the inverse square law relationship, and finally we can experimentally verify the inverse square law for gamma radiation. So I hope you've enjoyed today's lesson on the inverse square law investigation for the nuclear physics topic of AQA A-level physics. Thank you very much for watching, and as always, have a lovely day. Hello and welcome to this video on the dangers of radioactivity, which is part of the nuclear physics topic in AQA A-level physics. So in today's lesson we're going to try and understand the impact of radiation on humans. So if we've been successful and learned in today's lesson, we should be able to identify the different units of radiation, look at how we can measure the effect of radiation in humans, and finally write a risk assessment for handling radioactive materials. Now this forms part of the AQA specification in 3.8.1.2, alpha, beta and gamma radiation, in particular looking at the applications and the background radiation. So the first unit of radioactivity we've got to consider is the becquerel. Now 1 becquerel is defined as the activity of a quantity of radioactive material in which 1 nucleus decays per second. So therefore the becquerel unit is equivalent to an inverse second. So 1 becquerel is 1 second to the -1. So the becquerel, which is the unit of pretty much disintegration, is named after Henri Becquerel, who shared a Nobel Prize with Pierre and Marie Curie in 1903 for their work in discovering radioactivity. Now it's important that at A-level physics we only assume that when a nucleus decays it will produce 1 radioactive particle. So this means the activity can also be defined as the number of radioactive particles produced every second by a sample. Now the next unit of radiation is the Gray. Now this is the SI derived unit of absorbed dose of radiation. So we define a Gray as the absorption of 1 joule of such energy by 1 kilogram of matter. Now the Gray was named after the British physicist Lewis Gray, who was a pioneer in the field of the measurement of radium radiation and X-rays and their effects on living tissue. So fundamentally the Gray measures how much energy is deposited into a mass via ionizing radiation. Now the final unit of radiation which we've got to be aware of is the sievert, which is the SI unit of effective radiation dose. So sieverts represent the biological effects of ionizing radiation. So when you've got to consider the biological effects of radiation, further calculations have to be performed to convert the absorbed dose of energy, which is given by the Gray, into an effective dose, which depends on the type of radiation and the biological context of where that radiation hits. Now the sievert is named after Rolf Sievert, who was a Swedish medical physicist renowned for his work on radiation dosage measurement and research into the biological effects of radiation. So you've got to be aware that the sievert differs from the Gray due to the type of tissue the ionizing radiation hits and the ionizing power of that radiation. So the Gray and the sievert units are both based on the measurement of the concentration of ionizing radiation absorbed per unit of a material's mass. So therefore this means that the Gray and the sievert will share the same SI unit. However, despite this commonality, the sievert and the Gray are only interchangeable for certain kinds of radiation. Now we state that the sievert has the units of joules per kilogram equivalent because the equivalent incorporates the features of human tissue and the type of radiation which haven't been mentioned prior to this. So we say that the Gray is used to express the physical quantity of the absorbed dose, which is the amount of energy absorbed per unit mass in any material, whilst the sievert is used to express the biological equivalent dose to human tissue. So as the sievert has a biological effects component to it, a corrective factor, which we call the weighting factor or radiation quality, is applied to convert the physical unit of the grey into the biological effects unit, that is the sievert. So we've got our absorbed dose, which is the grey, but when we incorporate our radiation weighting factor, which links into the type of radiation used, and we link it into the tissue weighting factor, the factor caused by where that radiation hits, it will turn your grey into the sievert. So the weighting factor depends on the type of radiation, type of tissue irradiated, and the type of radiation used. So we can link the units as follows. So the becquerels shows the activity of radiation, or how many decays there are per second. The greys act as a measure of how much energy the radiation has deposited per kilogram, whilst the sievert indicates the damage that radiation can lead into the typical human body. And you can convert between greys and sieverts with weighting factors due to the radiation type, where we know the greater the ionizing ability, the greater weighting factor, and the tissue with which the radiation hits. So here we can see in the following diagram the link shown between your becquerels, your greys, and your sieverts. Now, previously we have looked at the inverse square law, and we've looked at cobalt as a gamma emitter. Now we can say that the number of radioactive decays it carries out per second is on the order of about 10 to the 5, so this indicates the activity of the radioactive source is about 10 to the 5 becquerels. Now we know that each radioactive particle emitted by cobalt has an energy of about 10 to the minus 13 joules, so therefore it indicates to us that every second the source emits about 10 to the minus 8 joules, because we've got each particle with an energy of about 10 to the minus 13 joules and 10 to the 5 particles emitted every second. So this tells us that in a typical experiment you carry out in school, the source will emit about 10 to the minus 5 joules. Now it's important to note that if we assume that the entire energy is absorbed by a human of order of about 10 to the 2 kilograms, about 80 kilograms, okay, that's a sensible suggestion, if not an overestimation, then the radiation dose you would receive is about 10 to the minus 7 joules per kilogram, because it would be 10 to the minus 5 divided by 10 to the 2. So in a particular experiment you will receive in maximum about 10 to the minus 7 greys. Now if we assume that the part of the body which absorbs the radiation is the skin, and the radiation is solely gamma radiation, that considers our weighting factor, we get about 10 to the minus 6 sieverts. Now this is not harmful, but it's not insignificant, so precautions need to be taken. And remember, any exposure needs to be considered as a possible risk to ionization, because radiation is stochastic. There's no lower safe limit for the amount of radiation you can absorb. Now since ionizing radiation is stochastic, we've got to always consider the biological effects of any radiation, and this includes the biological effects of the background radiation found all around us. Now here you can see some of the measurements of the sieverts you receive each year from just living on the planet Earth. So as you can see, every human does receive a sizable body dose of radiation each year, which is just the background radiation found on the Earth. Now generally, to help you understand this diagram well, one sievert gives you a 5.5% chance of developing cancer. Now you can see by the values that we've got microsieverts and millisieverts that the background radiation is very unlikely to cause you to develop cancer. However, because radiation is stochastic, it is still possible because there's no lower safe limit. So there are many different sources of background radiation, and these include firstly the air, because radioactive radon gas is released from rocks and it emits alpha radiation. The concentration of this gas in the atmosphere varies from place to place, and it's usually the largest contributor to the background radiation. It also includes ground and buildings, because nearly all rocks contain radioactive isotopes. It includes cosmic radiation, because cosmic ray particles, mainly high energy protons from space, can lead to radiation being produced, because they will collide with particles in the upper atmosphere of the Earth, producing this nuclear radiation. Another source of background radiation is living organisms, because all plants and animals contain carbon, and some of this will actually be the radioactive carbon-14 isotope. And finally, we've got artificial radiation. Radiation radiation from medical and industrial sources, which will make up a small amount of the background radiation. So on Earth you are surrounded by particles giving off radiation. Indeed, most substances and objects are radioactive. They do emit ionizing radiation. Now humans give off ionizing radiation themselves, typically about 7,000 becquerels. However, most of the resultant ionizing radiation is absorbed within the owner's own body, so actually the human doesn't actually release as much ionizing radiation as 7,000 becquerels. So we've got to consider a few things with these ideas. Do we define every substance which gives off radiation as radioactive? Do we have to treat all substances which give off radiation with the same safety procedures, and are humans actually classed as radioactive? So, what do we define as radioactive, and what criteria do we place on an object to make it radioactive? So the Radiation Protection Division of the Health Protection Agency defines a radioactive substance as having an activity of 400 becquerels per kilogram. So for the typical mass of a human being about 70 kilograms, we can say that it has to have an activity of about 100 becquerels per kilogram. So therefore it's not actually radioactive, but because we're below this lower threshold, because whilst the threshold for being radioactive is 400 becquerels per kilogram, a human has an activity of 100 becquerels per kilogram. So humans do not need to be treated with radioactivity safety measures. Now when we're considering background radiation, you've got to remember that when you take a reading of the count rate from a radioactive source, you must measure the background radiation count separately and then subtract it from your measurements. Now to do this accurately, you've got to take at least 3 readings of the count rate using a Geiger counter without a radioactive source present. You then average these readings and subtract this average from each measurement you take of a radioactive source's count rate. So you would have the total count rate, which is just everything with the radioactive source and the room it is in. You can then work out your corrected count rate by subtracting the background radiation from that. So since it's believed that there's no limit below which ionizing radiation is harmless due to the stochastic nature of radioactivity, it's recommended that exposure to ionizing radiation should be as low as reasonably practical or achievable. Now we abbreviate this to ALARA, as low as reasonably achievable, and we need to consider how to achieve ALARA status when using radiation. So you've got to always remember that there is some risk with using radiation. Now never state in an examination that you've removed a risk, you've only ever reduced the risk. Now evidence for this fact that there's no low safe limit comes from studies of long-term health of survivors of nuclear disasters such as Chernobyl. So let's look at some guidelines. Firstly, radioactive materials must be stored and used with care to prevent contamination or radiation poisoning, a form of radiation. So you must be aware of the guidelines in place from the government to safely store and use radioactive materials. Again, materials with an activity greater than 400 becquerels per kilogram. So the first rule is the storage of radioactive materials in a lead-lined container. Now most radioactive sources will produce gamma radiation as well as alpha or beta. Now the lead lining of the container must be thick enough to reduce the gamma radiation from the sources in the container so it goes to the level of the background radiation. The second rule is that regulations require that containers are under lock and key and the storage facilities are checked to see if they are effective in reducing radiation. So it tends to be that many sources are kept in a lock room in an office. Now in schools there's someone called an RPS, a radiation protection officer, who is in charge of checking the radioactive sources, which is done once a year, and they're going to fill in a form regarding this which is sent off to the National Standards Agency. Rule 3 is that no source should ever come into contact with your skin. So solid sources should be transferred using tools like tongs, like a glove box, like a robot. So this ensures that the distance between the source and the experimenter is practical, yet the intensity of gamma radiation is low and the user is beyond the range of alpha and beta. The fourth rule is that radioactive liquids, gases and powders are held in sealed containers. Now this ensures that the gas can't be breathed in and the radioactive liquid or powder cannot be ingested. Then in rule 5 is that radioactive sources should not be used for longer than necessary, because the longer a person is exposed to ionizing radiation, the greater the dose of radiation received. Now if the 5 rules, the 3 rules including the using and 2 the storing are followed, then a law will be achieved. So if we have learnt in today's lesson, we should be able to understand the applications of handling radioactive sources, understand background radiation, examples of its origins, and experimental elimination from calculations. So if we've been successful and learnt in today's lesson, we should be able to identify the different units of radiation, look at how we can measure the effect of radiation in humans, and then finally write a risk assessment for handling radioactive materials. So I hope you've enjoyed today's lesson on the dangers of radioactivity, which is part of the nuclear physics topic in AQA A-level physics. Thank you very much and have a lovely day. Hello and welcome to this lesson on the decay constant, which is part of the nuclear physics topic in AQA A-level physics. So in today's lesson we're going to try and explain the nature of radioactive decay and understand this concept of the decay constant. So if we are successful and we learn in today's lesson, you should be able to define exponential decay in terms of radioactive decay, explain why radioactive decay is a random process, and then define and calculate the decay constant of the nuclear decay. So in today's lesson we're going to be covering the following part of the specification: 3.8.1.3 radioactive decay. So exponential behaviour in physics is actually very common, and it appears in the physics A-level specification several times. Now examples of this include the discharge of an electrical charge on a capacitor whose plates are connected via a resistor, the reduction in amplitude of a damped simple harmonic oscillator, the absorption of electromagnetic radiation passing through matter, so for example gamma rays through lead, Newton's law of Coulomb, and then finally the radioactive decay of unstable nuclei by the principle of half-life. So exponential behaviour can be proven if the constant found in the equation is the same whenever values are inputted into the equation. So we can prove this if the y value is expressed as 1 over the square root value, and a straight line can be drawn from our experimental data. Now in most cases exponential behaviour is observed as radiation and particles spread out via a sphere, and the surface area of the sphere is 4 pi r squared, so given a constant rate of change, the exponential behaviour. But another way in which we can observe exponential behaviour, which isn't linked to the idea of particles and radiation spreading throughout a sphere, is in radioactive decay. So radioactive decay is the process of a nucleus changing in composition to increase stability. So radioactive decay will involve the increased instability of the nucleus, and it can lead to the emission of either alpha, beta or gamma radiation. Now this increase in stability is due to an increase in the comparative strength of the strong force, because an unstable nucleus has the electromagnetic and strong interactions as similar sizes in this nucleus, whilst a stable nucleus has a strong interaction much more dominant than the electromagnetic interaction. Now it's impossible to measure if an individual nucleus will decay in this process because it is random. However, we can measure the time it takes on average for an unstable nucleus to decay, and this is linked to a quantity called half-life. Now the half-life of a radioactive isotope is the average time it takes for either the mass of the radioisotope to drop to half its original mass, the count rate of the radioisotope in a sample to fall to half its initial value, or for the activity of the radioisotope in a sample to fall to half its initial value. Now in practice, half-life is not measured by counting nuclei, but by measuring the time it takes for the activity to halve. So for example, if the count rate is 600 counts per minute and it takes 30 minutes to go to 300 counts per minute, that's the half-life, 30 minutes, so it'll take a further 30 minutes to go to 150 counts per minute. Now it's important that we always state that the half-life is the average time for the mass to halve, the count rate to halve, or the activity to halve, because radioactive decay is a random event. So for a substance we could measure how many radioactive nuclei there are, and over time the radioactive nuclei will become non-radioactive via radioactive decay. So over time more and more non-radioactive nuclei are produced via this decay. Now there are more produced at the start and fewer produced over time because this is exponential decay. Now it's important that radioactive decay is a random and spontaneous event. So it means that the individual behaviour of a nucleus cannot be predicted, nor could it be influenced. Now the chance of decay remains constant, which is why decay slows, okay, over time, because there are less radioactive nuclei to actually then become non-radioactive, and the chance of each one decaying is constant, so the number of nuclei decaying becomes less, okay, with each time, but the time it takes to half remains the same. So for a half-life is the same for each halving of the number of radioactive nuclei, count rate, or activity. So it's important to note that because the chance of decay happening is the same all the way through the process, regardless of how many there are, we've got the idea of half-life. So it's important to note that it is, it's a fixed value, and it's common throughout however the decays are, because it is the chance of decay happening is the same each time. Now we can have a more mathematical approach to determining the mass of a radioactive isotope, or the activity, or the count rate after a certain number of half-lives. So if we consider a sample of radioactive isotope R, which starts off with 100 grams of radioactive nuclei, after one half-life the mass remaining will be 50 grams, after two half-lives it'll be 25 grams, after three half-lives it'll be 12.5 grams, each time it's halving in size. So therefore we can use this idea to calculate a general formula for working out these values. Now we can do this for mass, we can do this for activity, we can do this for count rate. So what we say is the mass of the radioactive nuclei remaining is equal to 0.5 to the power of number of half-lives times by the initial mass. Now this could be for the count rate, or it could also be for the activity. Now, as well as working out values with this mathematical equation, you can also work out the half-life of a radioactive substance using an experiment and forming a graph where you plot the activity, or the mass of radioactive nuclei, on the y-axis and the time on the x-axis. Now because this is an exponential process, because the chance of decay is constant throughout, okay, this will always form an exponential decay curve. So what will happen is, on these decay curves you draw on the graph two lines where the activity, or the count rate, or the radioactive mass is half of the other. So for example, one line where the activity is 200 and the next line where the activity is 100. You then extrapolate these lines downwards and find the corresponding time, and the difference in the time is the half-life. So that's a very important idea. So here's an example. So we've got a graph here which shows an exponential decay. Again, why is an exponential decay? Because the chance of decay happening for each nucleus is the same, and the number of nuclei remaining after a prolonged time gets lower, so less will be decaying, but the proportion of them decaying will remain constant, leading to this exponential decay curve. So you choose the time for one activity and you choose the value. You then extrapolate down and find the time. You then find the time for the activity, which has half the value of the first activity. So in this case we've done 8,000 becquerels and we've done 4,000 becquerels. Now the half-life is the time taken between the first activity measured and the second activity measured. So in this case we would say the half-life will be 7 seconds, because that's the difference between the two values. Now this would be true if we had the mass of the radioactive isotope on the y-axis, or we had the count rate of the sample on the y-axis. Now we would also advise that you would take this value, you would work this value out for a number of different points in your data, and then calculate a mean. This again is to minimize the random nature of radioactive decay. So we would note that as the mass of the radioactive isotope, or the activity, or the count rate decreases with time, the graph is referred to as a decay curve. Now measurements show that the mass decreases exponentially. It drops by a constant factor of multiple and equal intervals of time, which is the same for the count rate or the activity. Again, why is that? Because each nucleus has the same chance of decaying. Now, although in theory the radioactive decay curve will never fall to zero, in practice the level of radiation falls to a level which is indistinguishable to the background radiation. Now, in previous concepts, when we've looked at radioactive decay, we can consider this on the scale of nuclei. So if we consider a sample of radioactive nuclei, we can use what we call a whole scale method. So we can look at not just one nucleus, but at actually a great number of them. So we can say that radioactive decay follows statistical mechanics. So this is easier to carry out, as it's easier to measure the macroscopic behavior in the real world, as opposed to just a sample of a very small number of radioactive nuclei. Which is why it's easier not to count the number of radioactive nuclei in a sample, but rather to measure the activity, or the count rate, or the mass. Now, like mentioned before, radioactive decay is completely random. You can't predict individual behavior, so we can't predict when the atom's nucleus will decay. Now, while you cannot predict the decay of an individual nucleus, if you've got a very large number of nuclei, we can look at the overall behaviour to show a pattern. So any sample of a particular isotope has the same rate of decay. The same proportion of the atomic nuclei will decay in a given time. So each unstable nucleus within the isotope will have a constant decay probability. So we can then use this idea, okay, to then calculate the statistical probability that one nucleus would decay in a set time. So like I said before, we should be able to calculate the chance, the probability that how long it would take for one nucleus to decay. So we can think what's the chance that this unstable nucleus will decay and become more stable, or what's the chance it will stay unstable. So this links to the concept of what we call the decay constant. That's the probability of an individual nucleus decaying and then becoming more stable over a set time. Now we normally state the decay constant in terms of how likely the nucleus is to decay in 1 second. So this means the higher the decay constant, the faster the rate of decay. So this is also based though on random behaviour and probabilities. So to fully understand radioactive decay, we've got to look at the idea of the decay constant. Now the decay constant, which is given the symbol lambda, is the probability or chance that an individual nucleus will decay in a second. Now lambda is used for wavelength as well as the decay constant, but the context that it's used in should make it unambiguous. Now the decay constant has units of becquerels or seconds to the -1. Now we can link in our previous understanding of things like activity and decay constant to give us the following equation. So because of the activity of a radioactive source is how many decays happen per second, we can combine this with the decay constant and the number of radioactive nuclei present. So we can say activity is equal to lambda times by n, because the probability for each of the unstable nuclei is lambda. Now A is the activity of the sample, there's the number of nuclei that decay every second. Now the decay constant is the constant of proportionality between the activity of the sample A and the number of unstable nuclei n in the sample. So what this tells us is that the higher the decay constant, the greater the chance of the nucleus decaying, so the greater the activity. So the higher the number, but also it tells us the higher the number of particles, the more decays taking place, so therefore the greater the activity. So the decay constant is a measure of how quickly an isotope will decay. So like we said before, radioactivity has the following equation. A is equal to lambda n. However, as time passes, n will get smaller because the number of radioactive nuclei will be decreasing. So A represents a decrease in n. So to make the formula reflect this, it does need a minus sign. So A is equal to minus lambda n. So the more undecayed nuclei you have and the greater probability that an individual one will decay, the greater the activity of the sample. So we can also refer to activity as the rate of disintegration. So the activity of a radioactive source is how many radioactive decays happen every second, which we can also express in terms of differentials. So A is equal to delta n over delta t, and we know that A is equal to minus lambda n. So we can equate those two values. So we can say delta n over delta t, the change in the number of radioactive nuclei in a certain time, is equal to minus lambda n. Now the unit of the decay constant, as mentioned before, is seconds to the -1. So a large value of the decay constant means that there's a fast radioactive decay and a short half-life, whilst a small value of the decay constant means there's a slow radioactive decay and a long half-life. So radioactive decay is an iterative process. The number of nuclei that decay in one time period controls the number that are available to decay in the next time period, leading to the equation you can see on the screen. Now we can plot out our decay curves to show the impact of the decay constant. So here you can see the number of radioactive nuclei n on the y-axis and the time t on the x-axis. Now the red line shows a small decay constant and the blue line shows a large decay constant. Now a small decay constant means there's a small probability of a nucleus decaying. So this will mean the half-life is longer when the decay constant is smaller. So this indicates to us that the half-life and the decay constant are inversely proportional, whilst the blue line shows a large decay constant and means there's a high probability of decay. So this means that the half-life is shorter when the decay constant constant is higher. This makes sense because there's a greater chance of decaying, so they'll decay more rapidly, so our half-life takes up a shorter time. Now the half-life and the decay constant are inversely proportional. Now in an upcoming session, we'll look at the mathematical link between the decay constant and the half-life, in addition to the qualitative relationship we've just covered. Now we'll also look at ways in which the decay constant can be derived by mathematical or graphical methods. Now this will involve taking logarithmics of values, which was similar to when we looked at this idea in capacitors. So to summarise what we've learned in today's lesson, we can understand what the random nature of radioactive decay is, understand the constant decay probability for a given nucleus, understand the equation that delta n over delta t is equal to minus lambda n, and the use of activity is A is equal to lambda n. So if we've been successful, we can define exponential decay in terms of radioactive decay. We can explain why a radioactive decay is a random process, and we can define and calculate the decay constant of nuclear decay. So I hope you've enjoyed today's lesson on the decay constant, which is part of the nuclear physics topic in AQA A-level physics. Thank you very much for listening, and have a lovely day. Hello and welcome to today's lesson on Rutherford scattering, which is part of the nuclear physics topic in AQA A-level physics. So in today's lesson we're going to look at how we can detail the discovery of the nucleus. So if we've been successful today and we've learnt in this lesson, we should be able to describe how the nucleus was discovered, explain why the nucleus was not discovered earlier, and finally work out how close the alpha particle can get to the nucleus in Rutherford scattering. So in today's lesson we're covering the following part of the AQA A-level physics specification. 3.8.1.1 Rutherford scattering. So you must have an appreciation of how the knowledge and understanding of the structure of the nucleus has changed over time. So to look at this, we will start at what we originally thought was the smallest particle in the universe, the atom. So the first model of the atom came from the chemist John Dalton. So John Dalton's atomic theory was that atoms are indestructible and indivisible, and they can't be divided into any smaller particles. Now Dalton's model is good for explaining the ideas of compounds, elements and mixtures. However, in 1897 the electron was discovered and found to be inside atoms. This meant we needed to amend this model of the atom, because scientific models have to be changed if the experimental results show that the previous model is wrong. So a new scientific model is created which can explain the experimental results. So just to clarify, a scientific model is an idea or theory which is used to explain observations and data made in experiments. So with this, J.J. Thomson replaced the Dalton model with something called the plum pudding model, because when J.J. Thomson discovered the electron, Dalton's model of the atom was no longer acceptable because there was now something inside of the atom. So Thomson believed that the atom was made of positively charged matter with negatively charged electrons scattered throughout like plums in a plum pudding, or chocolate chips in a chocolate chip cookie. So the plum pudding model was the first attempt at redefining what an atom looked like. So scientists were desperate to see if the plum pudding model was correct. So like said before, in the theory of the plum pudding model, Thomson realised that the plums, or the chocolate chips, were the negative electrons whilst the solid filling was a positive charge. In this idea, the atom is completely solid and there's no space in the atom. So it's important to note that we don't refer to protons in the plum pudding model, only positive charge, and that in this model the atom is completely solid. There is no space at all in our atom for the plum pudding model. So this model was used to explain the experimental observations of electrons. This model also explained why the atom was electrically uncharged. So just please do remember in this plum pudding model that there was no space inside of the atom. Now, please note as well that the atom consists of both positive charge, and electrons. So with our new observations and data, we could then amend our previous model to make our new model which did explain our new observations of the electron, because please remember that a new model is always proposed if we need to explain new observations and data. So J.J. Thomson's plum pudding model was a very, very important concept in the history of particle physics, because it's our first guess at how the atom was constructed. So Thomson's plum pudding model is what we believed the atom was until the director of particle physics at the University of Manchester, Ernest Rutherford, came along. So he carried out the gold foil experiment, or the Rutherford scattering experiment, in 1910 to test out whether the plum pudding model was true. So he bombarded thin gold foil with beams of alpha particles, and he expected it to be just like firing bullets at tissue paper. The famous quote was, "If the positive charge was evenly spread out, like Thomson said, then the beam should easily pass through." So what happened in this particular test to look at the structure of the atom? So Rutherford got a layer of gold foil 1 atom thick. Now in reality it wasn't 1 atom thick, but a couple of hundred of atoms layer thick, because it's very difficult at a 1 atom thick layer. So what happened then is Rutherford got a source which emitted alpha particles. So the positively charged alpha nucleus, was fired from a radiation gun such as uranium. Now at this point, alpha radiation was a new discovery of science. So alpha radiation is a type of radiation emitted from the nucleus which increases the stability of the nucleus. So as well, we know that alpha radiation is ionizing, which means it can ionize your DNA, which can mutate your DNA and can lead to cancer. So this alpha particle source is important because it emitted alpha particles which are made of 2 protons and 2 neutrons, commonly called the helium nucleus. So this meant the alpha particle had an overall positive charge. Now Rutherford placed these gold foil and the alpha particle source in a vacuum, and he fired the alpha particles at the gold foil. Now it's important to use a vacuum chamber because alpha particles would be ionized if there was air in between the alpha particles and the gold atoms. They would stop within about 5 centimeters of air. So if there was no vacuum chamber, then the alpha particles would never even have reached the gold atoms. And in addition, the alpha particles must be all traveling with the same kinetic energy, otherwise the results of the investigation would be invalid. Now Rutherford then placed an alpha particle detector beyond the gold foil, and then Rutherford moved the angle of the alpha particle detector and then fired the alpha particles of the gold foil and measured what happens to the alpha particles after they pass through the gold foil. So he moved it around into different positions. Now Rutherford expected that the fast moving alpha particles should smash straight through our plum pudding model atoms, because Rutherford expected this because the alpha particles are fired out of the radiation gun, the uranium, at a very fast speed, whilst the gold atoms are considered stationary. So he thought it would be like an artillery shell being fired through a piece of tissue paper. They just smash all the way through. But what did happen when Rutherford fired the alpha particles at the gold foil? So Rutherford found that most alpha particles passed straight through the gold foil like expected. Now this actually happened because the gold atoms are predominantly empty space. So the first conclusion is that the atom is mostly empty space. Now a few of the alpha particles deflected away as they passed through. Now the alpha particles are always deflected away from the nucleus. Now the nucleus will also recoil slightly in the movement, but this is much smaller due to the larger mass. This occurs due to the conservation of momentum. Now why do we get this repulsion taking place? Well, we get this repulsion taking as there must be a positive charge in the atom, because the positive charge of the atom and the positive charge of the alpha particle must be repelling each other. So the second conclusion was that the nucleus of the atom must be positively charged. Now it was later realized that the positive charge of the atom could be broken down into smaller units or particles, which were named protons. Now, like mentioned before, for the fast moving alpha particles to be deflected by the nucleus, the alpha particles must be striking something much more massive than themselves, which indicated that most of the mass of the atom must be found in the nucleus, because we must have the conservation of momentum, that when this deflection occurs, that most of the mass must be inside the nucleus of the atom. Now the last thing is that 1 in 10,000 alpha particles reflected backwards off the atoms. Now they do not literally reflect, rather they repel each other without touching, which we call backscatter. Now this occurs due to the large repulsion between the positively charged alpha particles and the positively charged nucleus. This occurs as the alpha particle would be directly contacting the nucleus, it would hit dead on. Now because 1 in 10,000 alpha particles will reflect backwards, and the only alpha particles that will be hitting dead on, this indicates that the nucleus itself cannot be that large, but we should really talk about these things in terms of nuclear radius and atomic radius. So because only 1 in 10,000 alpha particles will backscatter in this particular experiment, this indicates that whilst the nucleus has a positive charge and is extremely massive, it must have a very small radius. So this showed us that the nucleus of the atom must have a much smaller radius compared to the actual atomic radius itself. So the third conclusion is that the radius of the nucleus is much smaller compared to the radius of the atom. We actually believe that the nuclear radius is about 10,000 times smaller than the atomic radius. Now we can compare these results with the expected results if the plum pudding model was true, and the experimental results do not fit the old model. So this meant that Rutherford had to come up with a new model to explain the results. So Rutherford devised a new scientific model which explains the observations of his experiment. So because most alpha particles pass straight through the nucleus, straight through the gold atoms, it indicated to us that the atom is mostly empty space. Secondly, because most of the alpha particles are reflected when they pass near the center of the gold atom, the nucleus must be positively charged. And finally, because about 1 in 10,000 alpha particles were deflected by more than 90 degrees, the diameter of the nucleus is about 10,000 times smaller than the diameter of the atom, which is very, very important to understand. So to explain these results and observations, a new model of the atom was proposed. Firstly, inside every atom is a nucleus, and the nucleus contains all of the mass of the atom. It contains all of the positive charge of the atom, and is a very, very dense material. It's a very, very dense object. So we can say that the nucleus contains most of the mass, yet has a radius 10,000 times smaller than the atom. Now, the results from our Rutherford experiment, our alpha particle scattering experiment, led to the conclusion that the mass of the atom was concentrated at the center in the nucleus, and the nucleus was charged. So this nuclear model replaced the plum pudding model. Now later, Niels Bohr adapted the nuclear model by suggesting that electrons orbit the nuclei at specific distances, which was an amendment because the theoretical calculations of Bohr agreed with the experimental observations. Now later experiments led to the idea that the positive charge of any nucleus could be subdivided into a whole number of smaller particles, each particle having the same amount of positive charge. Now the name proton was given to these particles. Now if the nucleus was only made from protons, you'd expect massive nuclei to have very high charges compared to low mass nuclei, but the charges were observed to be much lower than expected. So Rutherford proposed the idea of a proton-electron doublet being part of the nucleus in 1920 to help explain this observation. He didn't realise it at the time, but he was actually referring to the nucleus with the idea of the neutron. So what happened was the experimental work of James Chadwick provided the existence to show that the neutrons must exist within the nucleus, and this was about 20 years after the nucleus became an accepted scientific idea, in 1932. So in looking at the Rutherford scattering experiment, we should be aware of, firstly, the conditions of the experiment, secondly, the results of the experiment, and thirdly, the conclusions of the experiment. Now with this work, Rutherford had worked out the density of the nucleus and the charge of the nucleus, but he had also estimated the radius of the nucleus in this experiment. So how can we use the Rutherford scattering experiment to calculate the radius of the nucleus? So to understand how Rutherford derived the nuclear radius, you've got to consider the conditions of the investigation and consider an alpha particle moving to hit towards the nucleus. Now in this derivation, we assume the nucleus is not moving at all. Now the alpha particle has a kinetic energy and is moving since it's being projected from a radiation gun. Now a radiation gun, like mentioned earlier, is a name given to any substance which emits radiation. Now as the alpha particle approaches the nucleus, repulsion occurs as both objects are positively charged. Now the interaction of the electromagnetic force between the particles causes the energy stored to change. So what happens is the alpha particle and nucleus are held stationary due to electrical potential energy, because the alpha particle and the nucleus are repelling each other due to similar positive charges. So So what will happen is that the kinetic energy at the start of the experiment will turn into electrical potential energy. So due to the conservation of energy, we can state that the kinetic energy at the start of the investigation equals the electrical potential energy at the end of the investigation. So the initial kinetic energy of the alpha particle will transfer to the electrical potential energy. So we can substitute in the equations for kinetic energy and electrical potential energy into this particular equation. So we know that the kinetic energy equation from GCSE physics is a half mv squared, and from the electrical fields module we know that the equation for electrical potential energy is Q1 Q2 over 4 pi epsilon squared r. Now we can rearrange this equation to make r radius the subject, so we can therefore work out what r is going to be, and we can then substitute also in the kinetic energy term, and we can therefore say that r is equal to Q1 Q2 over the kinetic energy times by 4 pi epsilon 0. Now this is an important idea because this was actually the first estimation derived for the nuclear radius in physics, but this radius that you would calculate with this equation is an overestimate, as it's not the actual size of the nuclear radius, rather it's the distance that the alpha particle gets to the nucleus before stopping. So it's actually dependent on the initial kinetic energy of the alpha particle, which wouldn't be the case if you were actually measuring the nuclear radius itself. So this radius that you're calculating in this particular equation is a maximum possible value of the nuclear radius, not an accurate value. So this radius of the nucleus calculated is actually better known as the distance of closest approach. It's the closest distance the alpha particle can get to the nucleus before it's backscattered. Now, we can derive the distance of closest approach by firstly working out the kinetic energy of the alpha particle, then secondly working out the potential energy of the repulsion, which has a radius term in it, then equating the two values and solving for the missing r term. Now Rutherford did carry out this calculation in 1905 when he carried out his Rutherford scattering experiment, and for gold, which has a charge of 79 times by 1.6 times 10 to the minus 19 coulombs, and then he solved this to get us a radius of 4 times 10 to the minus 14 meters. He then compared this with the diameter of the gold atom, which was measured to be about 3 times 10 to the minus 10 meters. So for the first time, Rutherford had actually estimated that the nucleus of the atom must have a radius 10,000 times smaller than the atom itself. So this meant that the atom is mostly empty, which is what we thought earlier when most of the alpha particles went straight through. Now it's very important to emphasize that this calculation gives an upper limit on the size of the gold nucleus. We cannot say that the alpha particle touches the nucleus and a more energetic alpha particle might get closer still, but what it does mean to us though is that this was the first calculation which indicated to us that the atom is mostly empty, which is why most of the alpha particles went straight through. Now, like we previously said, the nucleus and the alpha particles repelled each other, but what is this repulsive force? Well, this repulsive force is the electrostatic repulsion. It's Coulomb's law, because they've got two positively charged objects, so we can use Coulomb's law to calculate the force between the alpha particle and the positive charge in the gold atom. So we can also say that the actual repulsive force experienced by the alpha particle and the nucleus is equal to Q1 Q2 over 4 pi epsilon 0 r squared, where Q1 is the positive charge of the gold atom, which is 79 times by 1.6 times 10 to the minus 19. Q2 is the charge of the alpha particle, which is 2 times by 1.6 times 10 to the minus 19, and r is the distance of closest approach between the nucleus and the alpha particle. So if we've learnt in today's lesson, we should be able to have a qualitative study of Rutherford scattering and appreciation of how the knowledge and understanding of the structure of the nucleus has changed over time. Now, if we've been successful and learnt in today's lesson, we should be able to describe how the nucleus was discovered, explain why the nucleus was not discovered earlier, and we can work out how close an alpha particle can get to the nucleus in the Rutherford scattering experiment. So I hope you've enjoyed this lesson on Rutherford scattering, which is part of the nuclear physics topic in AQA A-level physics. Thank you very much for watching and have a lovely day. Hello and welcome to this lesson on nuclear instability, which is part of the nuclear physics topic in AQA A-level physics. So in today's lesson we're going to look at discussing the different types of radioactive decay. So if we've been successful and learnt in today's lesson, we can discuss what you can deduce about radioactive isotopes from an NZ graph, detail how a nucleus changes with radioactive decay, and then explain why naturally occurring isotopes do not emit beta plus radiation, which is part of the nuclear instability topic 3.8.1.4 in the AQA A-level physics module Nuclear Physics. So in nuclear decays, nuclei change from unstable nuclei into stable nuclei. Now most processes have this carry out via the weak interaction. So in this case, the W boson is passed from the unstable nuclei to its more stable products. Now the decay process lessens the impact of the electromagnetic interaction and increases the strong interaction. The only exception to this is alpha decay, which doesn't involve leptons or particles changing type, so therefore it decays via the strong interaction. But once again, this decay process lessens the impact of the electromagnetic interaction and increases the strong interaction. So we've got this alpha decay occurring with a very fast interaction. Now in our previous examples we've considered radioactive nuclei to be an unhappy face. However, in reality it's more appropriate to say an unstable radioactive nucleus is like a bubbling volcano. It's constantly churning and turning, waiting to erupt and become more stable and emit a form of radiation. So a slight change in the energy or the configuration of an unstable nucleus will cause radioactive decay. But what causes instability and what interactions are found in the nucleus? So there are two interactions which affect the stability of a nucleus. You've got the strong interaction, which causes attraction between all nucleons in the nucleus, and the electromagnetic interaction, which causes repulsions between all the protons. So to achieve a stable nucleus, the strong interaction must be much larger than the electromagnetic interaction, because remember, in a stable nucleus the strong interaction must be a lot greater than the electromagnetic interaction, because the strong interaction causes attraction between all the nucleons, whilst the electromagnetic interaction causes repulsion between all the protons. Now nuclear instability occurs when the strong interaction and the electromagnetic interaction are very similar in size. Now it's important to note that if the electromagnetic interaction was larger than the strong interaction, the nucleus wouldn't even form. So every nuclear decay tries to increase the magnitude of the strong interaction compared to that of the electromagnetic interaction. Now a nucleus will become unstable if it either has too many neutrons, too few neutrons, too many nucleons in total, or just has too much energy. Now physicists were fascinated to see if there were any trends in nature to show which nuclei were stable and which were unstable. So physicists surveyed all known isotopes of substances on Earth, and from this they plotted an NZ graph. So in this graph the neutron number is placed on the y-axis and the proton number is placed on the x-axis. Now these values were considered as the number of protons and neutrons can show the strength of the strong and the electromagnetic interactions. So we can look at the stability of isotopes by looking at an NZ graph. Now remember, just to clarify, N is the number of neutrons, not the number of nucleons, while Z is the number of protons. So on this graph we can plot the NZ line, which is when the number of neutrons equals the number of protons, and it's just a straight line through the origin. Now on the NZ graph we can also show a belt of stability. Now the stability belt is the region on the NZ graph where there are stable isotopes. So for lighter isotopes the stability belt is where N equals Z, when you have the same number of neutrons as protons, whilst for heavier isotopes the stability belt is when N is greater than Z, so therefore there are more neutrons compared to protons. Now if an isotope is not in the stability belt, it will be an unstable isotope, and the region the isotope is found on the NZ graph shows the type of decay it will carry out. So it could be placed above the N equals Z line, beyond the N equals Z line, below the N equals Z line, and all these isotopes carry out different decays as they're found on different places on the graph. Now all unstable isotopes will decay to try and get onto the stability belt. So here's an example of the NZ NZ graph. Now, most NZ graphs show a simplified version of possible radioactive decays, and they tend to focus on the beta particle emitters. This is because beta decay is the main decay carried out by the more common lighter elements. Now, a more detailed NZ graph will show the stability belt for the isotopes, and that when a radioactive decay occurs, the isotopes shift towards the stability belt. So, what trends can you spot on the NZ graph, and where are the different types of emitters of radiation? So you can work out the nuclear decay from the isotope's position on the NZ graph. So there are several types of decay modes that an unstable nucleus can undergo. Now, alpha emitters occur beyond Z equals 60, most of them found at Z equals 80 or above. These nuclei are too large to be stable, as there are too many protons, so the electromagnetic force is too large, as the strong force is too spread out in that large nucleus. Beta minus emitters are found to the left of the stability belt. These isotopes are neutron rich compared to the stable isotopes, whilst beta plus emitters are found to the right of the stability belt. These isotopes are proton rich compared to the stable isotopes, and this is actually the same area as which electron capture occurs as well. Now, isotopes with too many protons compared to neutrons can carry out beta plus emission, or they can carry out electron capture. So electron capture is in competition with beta plus decay. Electron capture causes an outer shell electron to drop into the inner shell to replace the electron captured. This then carries out de-excitation and releases a gamma photon. Now, it's important to note that gamma emitters cannot be displayed on this graph, as the number of protons or neutrons do not change due to this particular emission. But what are the different emission processes? So the first one is alpha decay. So alpha decay is when two protons and two neutrons are lost from the nucleus when it emits an alpha particle. So this means the atomic mass number decreases by 4 and the atomic number decreases by 2. So a new element is formed that's 2 places lower in the periodic table than the original element. So alpha emission is when an alpha particle or helium nucleus is ejected from the parent nucleus. Now, this must mean there's a new element formed, since there are a different number of protons in the main nucleus. Now, whilst alpha is the same as a helium nucleus, the term alpha is used if that particle originates from the nucleus of an atom. Now, because we're forming a new element in alpha emission, it is an example of transmutation. And like mentioned before, the element is formed in alpha decay 2 places lower on the periodic table than the parent element. Now, each alpha particle is released with the same kinetic energy as no other products are produced in the decay. So here's a demonstration of alpha emission. The next type of emission is beta decay. Now, in beta minus decay, a neutron changes into a proton plus an electron. The proton stays in the nucleus and the electron leaves the atom with high energy as a beta particle. Now, the atomic mass number in this case will stay the same, whilst the atomic number increases by 1. So in beta minus decay, the nucleus has 1 more proton and 1 less neutron when it emits that beta particle. So it can produce a new element 1 place higher in the periodic table. So in beta minus emission, a neutron is transformed into a proton that stays in the nucleus, and an electron and an antineutrino, which are both emitted. Now, beta minus emitters are found naturally in the universe, and they can be manufactured when stable isotopes are bombarded with absorbed neutrons. Now, again, beta minus is an example of transmutation because a new element is formed since there are a new number of protons in the nucleus. Now, whilst a beta particle is the same as an electron, the term beta is used if the particle has originated from the nucleus. Now, the element formed in beta minus emission is found 1 place higher on the periodic table compared to its parent nucleus. Now, like we mentioned before, beta minus emitters are found naturally in our universe, and here is a demonstration of beta minus emission. Now, beta plus emission is when a proton is transformed into a neutron and a positron along with a neutrino. So the opposite beta decay process occurs to beta minus decay. Now, again, a new element must be formed since we've got a new number of protons in our parent nucleus, and the term beta is used because this particle originates from the nucleus. So this is another example of transmutation, but in this case the element formed is found 1 place lower on the periodic table compared to the parent nucleus. Now, beta plus emitters are not found naturally in the universe. They can only be manufactured with stable isotopes being bombarded and absorbing protons. Now, in gamma decay, there's no change in the makeup of the particles, they just lose energy in the form of photons. So alpha emission is often followed by gamma emission, and the daughter nuclei are left in an excited state from the alpha emission, and then at some point they fall from the excited state to the ground state, emitting a gamma photon. So there's no nuclear structure change, just a change of energy. So this is not an example of transmutation, as no new element is formed. So a nucleus which has excess energy before gamma decay is in what we call a metastable state. So here is a demonstration of gamma ray emission, and it's important to note that gamma ray emission will only occur after alpha emission. Now, the next type of nuclear decay is electron capture. So in electron capture, a nucleus can capture one of its orbiting electrons, and a proton then will change into a neutron, okay, and you will also get an emission of a neutrino. Now, this has the same overall effect as a beta plus emission. So again, it's an example of transmutation as a new element is formed. Now, also remember that when you carry out electron capture, you will also produce a gamma photon due to de-excitation, and a neutrino due to lepton number conservation. Now, electron capture does not increase stability for a nucleus as much as beta plus emission, but requires less energy to carry out the process. Now, electron capture will produce a new element one place higher in the periodic table than its parent nucleus. Now, another example of a decay is a nucleon emission. So it's possible for an unstable isotope to emit a nucleon from its nucleus. So for example, in a proton-rich or proton-heavy nuclei, it's possible for a proton to be emitted. So again, you will lose one proton. So again, this is an example of transmutation as a new element formed, and the new element is formed one place lower on the periodic table. Now, in the other type of nucleon emission is when you emit a neutron. So in a neutron-rich or neutron-heavy nuclei, it's possible for a neutron to be emitted. But this time, it's not a case of transmutation, as no new element is formed, as you have the same number of protons. And in addition to the traditional decays of the nucleus, there is also a sixth nuclear decay, internal conversion. So internal conversion is a process in which a nucleus is in an excited state and can release its excess energy. Now, in internal conversion, all of this excess energy is transferred from the nucleus to an orbital electron through the electromagnetic force. The orbital electron is then ejected from the atom. Now, both internal conversion and beta decay will eject electrons from the nucleus, but there are differences between internal conversion and beta decay. Firstly, beta decay occurs by the weak interaction, whilst internal conversion occurs by the electromagnetic interaction. Secondly, beta decays will also produce either neutrinos or antineutrinos in the process. And beta decay will also produce a nucleus of a new element, as you've changed a neutron to a proton or vice versa, but internal conversion does not. In beta decay, electrons are emitted with a range of energies because you're also producing a neutrino or antineutrino, but in internal conversion, because you're not producing a neutrino or antineutrino, all the electrons have the same energy. In beta decay, the electron emitted will be from the nucleus, whilst technically in internal conversion, the electron is emitted from the shell. Now, we can represent all these different decays, whether it be alpha or beta or electron capture or neutron emission, proton emission, internal conversion, with a decay path diagram. So this shows how the neutron number and proton number change in a decay. Now, in reality, an unstable nucleus will undergo a number of different radioactive decays before it becomes stable, and we can show this on a radioactive chain decay diagram, which is a chain diagram is each decay is linked to the previous decay for that particular nucleus. Now, it's also interesting to note that in a true decay chain diagram, there are a variety of decay paths which an unstable nucleus can take, and the path the unstable nucleus will take is down to probability. And in addition, a comprehensive decay chain diagram will also include the half-life of this decay process. as seen in this diagram on the screen now. So what have we learned in today's lesson? We should hope to be able to state the graph of N against Z for a stable nuclei. You should be able to have possible decay modes of unstable nuclei, including alpha, beta plus, beta minus, and electron capture, and also indicate the changes in N and Z caused by radioactive decays and a representation in simple decay equations. So if we've been successful in today's lesson, we should be able to discuss what you can deduce about radioactive isotopes from an NZ graph, detail how a nucleus changes with radioactive decay, and explain why naturally occurring isotopes do not emit beta plus radiation. So I hope you've enjoyed today's lesson on nuclear stability, which is part of the nuclear physics topic in AQA A-level physics. Thank you very much for listening and have a lovely day. Hello and welcome to today's lesson on gamma ray emission, which is part of the nuclear physics topic in AQA A-level physics. So in today's lesson we're going to be able to detail the effect of gamma ray emission. So if we've been successful and learned in today's lesson, we should be able to detail how a nucleus changes with radioactive decay. Define gamma radiation, then describe what happens to an unstable nucleus that emits gamma radiation. So we're going to be looking at 3.8.1.4 nuclear instability. So let's consider the unstable nucleus 99MO42. Now this nucleus undergoes beta minus decay. So what would our decay equation be for this process? So we'd have this particular equation in terms of nuclei, our MO, our molybdenum, turns into technetium whilst emitting an electron and an antineutrino. Now we can actually visualize this decay in terms of particles. So you can see we've got our unstable nucleus turning into a more stable nucleus, an electron and an electron antineutrino. Now if we just focus on the change of the nucleus in the decay, we've got our starting or mother nucleus, and then we've got our finishing or daughter nucleus. Now in certain decays the daughter nucleus will have more energy for that nucleus than if that nucleus was just existing normally. So in this case we would say the daughter nucleus is said to be excited. So a nucleus is in an excited state when it's above the ground state, which is the state that a nucleus of this particular type would have normally. So in this example, technetium is excited, so this means that the nucleus of technetium contains more potential energy than it normally does. So in these types of decays, it's more appropriate to show the decay in terms of energy level diagrams. So energy transitions of nuclei during radioactive decays are shown with energy level diagrams. Now on an energy level diagram, the vertical axis shows the relative energy of each level. So the lower down the axis, the lower the energy of the nucleus. Now in this case the arrow is going down because the technetium is more stable but not completely stable, so it exists with less energy, so it's lower down on our energy level diagram. So we've increased our stability. Now it's not completely stable yet, it's just more stable than the starting nucleus at the beginning of the decay. So we would say in this case that the technetium nucleus is considered to be excited. So the technetium nucleus has less energy than the molybdenum nucleus, yet it will have more energy than when technetium nuclei exists normally. So what would happen to this excited nucleus? Well, what would happen is the nucleus in an excited state would eventually return to its ground state. Now this is represented on an energy level diagram as an arrow going down, as the ground state has less energy than the excited state. So when the nucleus transitions down to the ground state, a photon of energy is emitted, much like when an excited atom de-excites. Now to work out the energy of the photon emitted from the nucleus, we can use the same principle as discussed as when we looked at excited atoms. So the energy released in terms of the photon, which is equal to hf, because that is our equation for a photon energy, is equal to E2 minus E1. So it's the difference in energy from the excited state to the ground state. So the change in energy is equal to the amount of energy that is released in the decay. Now certain nuclei take a long time to transition down to the ground state. These excited states are called metastable states, literally translating into consistently unstable, and are denoted with an M on our energy level diagrams and our nuclear decay equations. Now, for example, in this case, the technetium stated below has a half-life of 6 hours, so it exists for some time in this excited state. Now, gamma emission should take a relatively short time to occur compared to alpha and beta emission, so metastability is measured against other gamma emissions. So as a note, in this case, it's all relative, because whilst it would exist in a metastable state for 6 hours, the molybdenum has a half-life of 67 hours. So you can see that actually this metastable state does not exist as long as the time would take for the beta decay to occur. Now, technically, a metastable state can be any isotope which has an excited state for longer than 1 nanosecond. So the most famous example of an isotope which exists in metastability is technetium-99. So technetium-99 is made when molybdenum undergoes beta decay. So this technetium remains in an excited state for some time. Like mentioned before, it has a half-life of about 6 hours before decaying by a gamma emission to the ground state. So therefore, we can say that this excited state of technetium is said to be metastable. So this technetium can be separated from the molybdenum and can be used in medicine, and its most common use is in a medical tracer. So metastable states are useful as those isotopes can be separated after their first emission and then can be solely considered a gamma source, because as you'll be aware, gamma emission can only happen after either alpha or beta decay. So if you don't want those products to be produced, you would have your metastable substance to be used as your gamma source, because they'll not emit any more alpha or beta because they've already done that. So like we mentioned in a previous lesson, the emission of gamma radiation does not change the position of a nucleus on the graph of n against z. However, there can be more than one possible route to the ground state through different energy level combinations. So this means that different nuclei can carry out the same transition to the ground state, but can produce photons with different energies. So our example here is the decay of magnesium into aluminium. Aluminium, the nucleus, is then still excited, and then it will decay into its ground state. But there are two possible routes of decay from the excited aluminium to the ground state aluminium. So as you can see, in the different possible routes, the total energy emitted remains constant. However, it can be split over a variety of gamma photons. So let's have a look at this example in a little bit more detail. So let's have a look at the possible gamma emissions which can take place after the aluminium has then been produced but is still excited. So there are two possible paths that the aluminium can carry out to de-excite and no longer be metastable. So path 1, as shown on the diagram on the screen, indicates that it could just emit one full photon of 1.02 mega electron volts, whilst you could also produce two photons, one of 0.19 mega electron volt photons, okay, and 0.83 mega electron volts of energy in that particular photon. So in the first pathway you could produce one photon, but in the second pathway you could produce two photons. So there's two possible ways in which the excited aluminium can decay into the stable ground state later on. Now, just to note that the total energy across both pathways is the same. So if you add up the two photons from that second pathway, they will equal the energy of the one photon in pathway 1. Now let's have a look at a few examples. So if we look at this particular example of cobalt decaying into nickel, okay, which of the following isotopes will emit the gamma photon? Well, it's the nickel that emits the gamma photons, as it's the nickel which is in the metastable state. So it wouldn't be true to say that the cobalt emits gamma photons. It's in fact the product in that original beta decay process, which is the nickel. The next question would ask, how many possible decay paths in this particular example does nickel have to de-excite? So the answer would be nickel has two possible paths to de-excite. It can either, okay, in pathway 1, go straight from 0.55 MeV all the way down to 0 MeV from your excited state to your ground state, or via pathway 2, it could do that in two steps. It could drop from 0.55 MeV to 0.38, and then from 0.38 MeV MeV to 0 MeV. So the next question could possibly ask you, what are the energies of the possible photons produced in this particular decay process? Well, by pathway 1, you would have one photon of 0.55 MeV being produced, because that's the difference between the excited state and the ground state, whilst in pathway 2, you'd have one photon of 0.17 MeV, which is the difference between 0.55 MeV and 0.38 MeV, and you'd have one photon of 0.38 MeV, which is the difference between the 0.38 MeV level and the 0 MeV level. Now to note, if you notice that in pathway 2, if you added those two photons up, they'd have the same energy as that one photon in pathway 1. Now, a more challenging question could ask you to work out the wavelengths of photons which could be possibly produced, which links us back into that first topic you did in A-level physics, particles and radiation. So pathway 1 will produce one photon of 2.26 times 10 to the minus 12 meters. How do you work that out? Well, you would say E equals HF. So therefore, if you know what E is, you would convert that into joules. You would then work out what the frequency is in hertz, and then use the equation C equals F lambda, where C is 3 times 10 to the 8 meters per second, to then work out what lambda would be. Remember, all these photons produced in this particular emission process are traveling at the speed of light, whilst you'd use the same methodology of pathway 2 and you get two photons, one of wavelength 7.31 times 10 to the minus 12 meters and another one of 3.27 times 10 to the minus 12 meters being produced. So what have we looked at in this particular lesson? We've looked at questions that may use nuclear energy level diagrams. We've looked at the existence of nuclear excited states, including gamma ray emissions and applications of this, such as the use of technetium as a gamma source in medical diagnoses. So if we've been successful and we've learnt in today's lesson to be able to detail how nuclei change with radioactive decay, define what gamma radiation is, and then describe what happens to an unstable nucleus that emits gamma radiation. So thank you very much for watching this lesson on gamma ray emission, which is part of the nuclear physics topic in AQA A-level physics. Thank you very much and have a lovely day. Hello and welcome to this lesson on the nuclear radius, which is part of the nuclear physics topic in AQA A-level physics. So in today's lesson we're going to look at how you can calculate the nuclear radius from experimental values. So if we've been successful and learned today, we should be able to detail how the value of the nuclear radius was discovered, understand how the nuclear radius equation was derived, and then detail how the nuclear radius equation allows us to understand nuclear properties, which links into the following part of the AQA A-level physics specification, 3.8.1.5 nuclear radius. So in previous lessons we've considered the size of the nucleus in an atom. Now Rutherford estimated the size of the nucleus in his Rutherford scattering experiment, where he found alpha particles at gold nuclei. So here an alpha particle was found near to the gold nuclei in the investigation. But what issues does this result have for the nuclear radius? Well, in this Rutherford scattering experiment, the alpha particle is repelled by the positive charge of the gold nucleus because it is also positively charged. So the kinetic energy of the alpha particle turns into electrical potential energy due to the repulsive force between the two charged objects. Now, this tells us that this value that we've calculated is not the nuclear radius, but in fact the distance of closest approach between the alpha particle and the nucleus. So this value could be changed with the energy of the alpha particle. So the more kinetic energy in the alpha particle, the closer it could get. So this tells us we're not actually measuring an accurate value for the nuclear radius. So we need a different way to measure the radius of the nucleus, because if we have a higher kinetic energy in our alpha particle, the nuclear radius in this instance will be smaller because the distance of closest approach will be smaller. So you can get a high distance of closest approach if you've got a low kinetic energy in your alpha particle, because there's less kinetic energy to change into electrical potential energy, so the conversion occurs further away from the nucleus. Whilst if your alpha particle has a high kinetic energy, you've got a small distance of closest approach because there's more kinetic energy to change into the electrical potential energy, so the conversion would occur closer to the nucleus. So this shows that we can't actually get one standard value for the nuclear radius by this this method because it depends on the kinetic energy in the alpha particle, so there must be a different way needed to measure our actual nuclear radius. So to work out the actual size of the nucleus, we can carry out an experiment called the deep inelastic scattering of electrons. Now this was known as the Davidson-Germer experiment and was conducted between 1923 and 1927, which confirmed both the de Broglie hypothesis and the nuclear radius. So by confirming the nuclear radius, the experiment was an important historical development in the establishment of the chain nuclear fission event, and by demonstrating the wave particle duality with the de Broglie hypothesis, this experiment was an important historical development in the establishment of quantum mechanics and of later the Schrödinger equation. So, the electron diffraction apparatus has a basic similarity with the alpha particle scattering carried out by Rutherford. So, electrons are fired at a thin film of atoms. In the first experiment, they used graphite. Now, electrons are used because they do not interact with the strong nuclear force of the nucleus, whilst neutrons, protons, alpha particles do, because electrons are leptons and are not hadrons. So, because of this case, the electron diffraction is an accurate method for measuring the nuclear radius, because they're not going to be influenced by the actual interactions produced by the nucleus. So in a similar fashion to the Rutherford scattering experiment, the electrons are fired at a thin sample of atoms and the path they take afterwards is then traced. So it's important to know what's going on. So the electron the electron can take a path which is influenced by two different factors. The electron path is influenced by both the scattering effect and the diffraction effect. Now this diffraction effect shows that the electrons have wave-particle duality, and the de Broglie wavelength of an electron to carry this out must be very small when we investigate our nuclear radius, so this means we've got to fire our electrons with a very high energy. So let's firstly look at the Rutherford scattering effects. So when the electron passes very close to the nucleus, the electrostatic force causes an attractive deflection of the particles. So this means that the pattern detected is similar to the one found in the Rutherford scattering. So the electrons deflect towards the nucleus, which is actually the opposite effect observed by Rutherford in his alpha particle scattering experiment. This deflection occurs because the negatively charged electrons are attracted to the positively charged nucleus. So even though the type of electrostatic attraction is different, the path pattern is actually the same as the Rutherford scattering results. The second effect is diffraction. So when the electron passes through the graphite structure, the electron gets diffracted. So for diffraction to occur, the electron must be exhibiting wave behavior. So the electron must have a de Broglie wavelength. So for the most diffraction possible, the gap between the actual graphite atoms must equal the de Broglie wavelength. So here the gap is actually the nucleus of the atom. So we can approximate the gap. We can approximate this gap to be between the nuclei because the diffraction takes place around the edges of the nuclei in which the electron wave moves between. So as the electron is acting like a wave for this diffraction effect, we can work out its wavelength with the following equation. The de Broglie wavelength is equal to Planck's constant times by the speed of light divided by the energy of the alpha particle. So actually the fact that diffraction occurs it shows us that Rutherford was actually very fortunate when he carried out his alpha particle scattering experiment, because unbeknownst to him that the de Broglie wavelength of the alpha particles that he used was actually quite small, and the Coulomb repulsion stops it getting too close to the alpha particle to diffract through. Now he was very lucky, because otherwise if you did get this diffraction effect in the Rutherford scattering experiment, this would have confused the data and he would not have been able to work out the nuclear structure which he carried out in 1911. So here we can see a graph of the electron scattering results gained when we fire electrons through our graphite structure. Now you'll notice the minimum angle, which is the dip in the graph, is important, as this must be the angle at which diffraction occurs. Now you can see you get your shape because our pattern is influenced by both the scattering effect, which is our curved line at the top right hand side, and our diffraction effect, which is our number of bumps or peaks, which is shown in the bottom right hand side. So this indicates to us that this bottom out, the first section, is the angle at which diffraction takes place. So we can use this measurement to then determine the gaps between the nuclei and therefore get a value for our nuclear radius. So please do remember that this overall pattern is a combination of both both the diffraction due to the de Broglie wavelength, but also the Rutherford scattering experiment. So the electron scattering clearly shows features of both Rutherford scattering due to the electrostatic interaction and diffraction. Now we can consider these results due to the diffraction of the electron that it must be exhibiting wave behaviour. So if we concentrate on the minimum we've pointed out earlier, it suggests that the nucleus is behaving as a circular object of diameter d. So we can use this to find a value of the nuclear radius, and we can use the diffraction equation which you've covered previously in our waves topic. So we know that sine theta is equal to lambda over d. Now please remember, this is a simplified version of the equation covered in the waves topic because there's no n term, because there are no orders of diffraction found here. It's just n equals 1. Now also, please remember that d is our nuclear radius and lambda is the de Broglie wavelength of the beam of electrons. Now we can further derive this equation to make it even more accurate, because by applying wave theory to plane waves passing through at normal instance through a circular gap, which is what we assume the nucleus is going to be like, we can get a correction term of 0.61, which we can apply to our equation, where we can say sine theta is equal to 0.61 lambda over d. But we've got to remember that if the minimum angle due to diffraction is measured and the de Broglie wavelength can then be calculated, then the nuclear radius can be found, which is given as d in the equation. Now remember, each high energy electron is diffracted by an individual nucleus. This isn't the same as electron diffraction covered in the particles and radiation topic, which is where electrons are diffracted between atoms. This is why our equation is for a minimum value and not a maximum value. So let's just recap our main methods to work out the nuclear radius. We have the Rutherford scattering method and we have the electron diffraction method. Now we've got to remember that for the Rutherford scattering method, it finds the distance of closest approach, whilst the electron diffraction method finds the nuclear radius. The Rutherford scattering finds alpha particles at gold nuclei, whilst electron diffraction has electrons fired at carbon nuclei. In Rutherford scattering, you get repulsive scattering due to the alpha particles and the gold nuclei having the same charge, whilst for electron diffraction, you will get attractive scatter as the negatively charged electrons are fired at the positively charged carbon nuclei. Now, Rutherford scattering relies on the particle properties of matter, whilst electron diffraction relies on the wave properties of matter. Now, Rutherford scattering has the major conclusion of backscatter, leading to the idea that the nucleus must be extremely small compared to the size of the atom, whilst diffraction is the major conclusion in the electron diffraction method, which shows us both electrons are acting as a wave and also allows you to work out the value of the nuclear radius. Now, electron diffraction can be used to measure the nuclear radius r for samples of various elements. Physicists then use this to find a relationship between R and the mass number of the element A, and this was carried out by plotting a graph of the nuclear radius R against the mass number A. And what we got is as follows. We found that if we plotted a graph of R against A to the power of a third, then this gives us a straight line through the origin with a gradient equal to a constant which we'll call R0. So plotting this graph can allow you to derive an accurate value of R0. Also, it's interesting to note that a graph of log r against log a gives a straight line with a gradient of a third and a y-intercept equal to r0, which confirms the relation between A and R is linked by a power of a third. Now this relationship is linked by a power of a third as the nucleus is a spherical shape and the volume of a sphere has a power of a 3 in it. Now we can also look at our graph of R against A. So for the experimental results we can see a graph of R against A plotted like the one below, and this shows us that R does not depend on A but rather A to the power of a third. So when they plotted the graph of R against A to the power of a third, they found a straight line that cut through the origin and had a gradient of R0. Now R0, by the way, is a constant representing the radius of a single nucleon and has a value on average between 1.2 and 1.5 femtometers. So we can say our equation we've got to learn is that the nuclear radius big R is equal to our constant R0 times by A to the power of a third, where A is the mass number of the nucleus. nucleus. So the radius of a nucleus has been found to be that particular equation where we can say for AQA examinations our standard value for R0 is 1.05 femtometers, where we say a femtometer is 10 to the minus 15 meters. Now it's also important to note that there's no standard value for R0 as it represents the radius of an average nucleon in a nucleus. Now there's no consistent value because there's different numbers of neutrons and protons in each nucleus, leading to a different average nucleon number. So let us have a look at how you would answer a question based on electron scattering experiments, because we can use our data to derive the nuclear radius. So for example, if the electron beam energy is 80 mega electron volts and the first diffraction minimum occurs at about 26 degrees, calculate the nuclear radius of a nucleus which diffracts the electrons. So the first step is converting your beam energy from MeV into joules. Now that conversion is by firstly converting MeV into EV, which is times by 10 to the 6, then multiply by 1.6 times 10 to the minus 19 to get it into joules. The second step is then to work out the momentum of the electron. Now the momentum of the electron is equal to P is equal to E over C, where C is the speed of light. So we can take our energy and divide it by the speed of light to get our momentum. We can then use this to work out the de Broglie wavelength of our electron, because we know that the de Broglie wavelength is equal to Planck's constant 6.63 times 10 to the minus 34 over the momentum which you've just worked out. Then finally we can then use the diffraction equation to derive our slit gap, which we can just say is our nuclear radius. So we say sine theta is equal to 0.61 lambda over d. So therefore d is equal to 0.61 lambda over sine theta. We know theta in this case to be 26 degrees. We've worked out the de Broglie wavelength lambda to be 1.6 times 10 to the minus 14 meters. Pop our value in and we get 2.2 times 10 to the minus 14 meters. Now a couple of things to note. In step 2 we did use a relativistic equation to work out our momentum, which may be the first relativistic equation that we have encountered, that P is equal to E over C. And then also please do remember that we were given our angle in degrees, so we've got to be using degrees here, so don't have your calculator in radians mode. So what can we summarise from today's lesson? We can estimate a radius of the nucleus from the closest approach of alpha particles and then determine our radius from electron diffraction. We should have knowledge of typical values of the nuclear radius and be understanding how the Coulomb equation can be used for the closest approach estimate. We can then understand our dependence of radius of the nucleon number with R equals R0 a to the power of third derived from experimental data. So if we've been successful and learnt in today's lesson, we should be able to detail how the value of the nuclear radius was discovered, understand how the nuclear radius equation was derived, and then finally detail how the nuclear radius equation allows us to understand nuclear properties. So thank you very much for watching today's lesson on the nuclear radius, which is part of the nuclear physics topic in AQA A-level physics. Thank you very much for watching and have a lovely day. Hello and welcome to this lesson on nuclear density, which is part of the nuclear physics topic in AQA A-level physics. So in today's lesson we're going to look at how to calculate the nuclear density from experimental values. So if we've been successful and learnt in today's lesson, we'll be able to calculate the nuclear radius of a nucleus with a derived equation, define the nuclear density of the nucleus, and finally calculate the nuclear density of the nucleus, which links into the following part of the AQA A-level physics specification 3.8.1.5, the nuclear radius. So once physicists had calculated the radii of various elements, they did ponder the following questions. How does the size of the nuclear radius affect the nuclear density? Which nuclear radius would have the bigger density, and why do you think that? So we could have either, uranium, the largest naturally occurring nucleus, and you could also have helium, the thing with the smallest nuclear radius with the presence of neutrons. So which of these elements would have had the bigger nuclear density and why? So physicists decided to theoretically find this out by deriving the equation for nuclear density. Now in this particular derivation they made one assumption, that the nucleus is perfectly spherical. Now this is reasonable considering that the nucleus is stable and the most stable shape we know in the universe is a sphere. So for an object to exist in the most stable manner, they must contain the lowest amount of potential energy, and this occurs when the nucleons are arranged in a sphere shape. So what we can do is that the previous electron scattering experiment calculated the nuclear radii of different nucleus. So we can then use the nuclear radius measurements to calculate the nuclear density of the nucleus. So if we have a nucleus consisting of A nucleons, we can assume that the mass of the nucleus is A times by U, where U is the atomic mass unit and V is the volume of the sphere. So we can say that density is equal to mass over volume. So we can substitute the volume of a sphere and the atomic mass into this particular equation. So we get that rho is equal to AU over 4 over 3 pi r cubed. Now in this particular equation we can substitute the nuclear radius that we covered previously. So we can now say that rho is equal to AU times over 4 over 3 pi r0 a to the power of a third all cubed. Now you'll notice here that we've got a to the power of a third and the entire actual value in the brackets cubed, so the power signs can cancel each other out. So now we can say that rho is equal to AU over 4 over 3 pi r0 cubed a, because again that a to the power of a third cubed will cancel those two things out. Now you'll notice on the top and the bottom of this particular equation there is the term of a, the number of nucleons. So the value for a cancels out in the equation. So we're left with rho is equal to U over 4 over 3 pi r0 cubed. So we know that U is the atomic mass unit and R0 is the average nucleon radius. Now you'll notice that this equation does not include the nuclear radius or the nucleon number. In fact, all of the values in the equation are constants. So this shows a couple of things. That firstly, the nuclear density is independent of the nuclear radius and the nucleon number, as neither appear in the equation, and also because all the values in the equation are constant, it indicates that all nuclei have the same density irrespective of size. So helium, the lightest neutron containing nucleus, and uranium, the largest naturally occurring nucleus, have in fact the same nuclear density. We can also show this because we know from our nuclear radius equation that r cubed is directly proportional to A and volume is directly proportional to A, because r cubed would link in like that. Now as the mass of each nucleon is approximately the same, this indicates that if the volume is constant and the mass is constant, it indicates that the density of nuclear matter will be constant. So what we can conclude is the following: that nucleons are separated by the same distance regardless of size of the nucleus and are therefore evenly separated inside the nucleus. So we can therefore conclude that because the nuclear density is constant, that you've got the same nuclear separation in all nuclei of all the elements in the universe. Now please remember that the nucleons in a nucleus have the same average separation. This is an average term due to there being two types of particles in the nucleus. Now a proton-neutron and a neutron-neutron only interaction will experience the attractive strong force, whilst a proton-proton will experience the repulsive electromagnetic force alongside the strong force, indicating there will be different separations inside the nucleus. So neutron-neutrons and neutron-protons are closer together than proton-protons. However, we do assume in this equation that the average nucleon separation is constant in the nucleus. So the value for average nucleon separation is the same for every nucleus in the universe. So all elements in the universe have the same separation between nucleons. So therefore all elements have the same nuclear density. So this means that when a nucleus changes its proton or neutron number, it changes the nuclear radius by the same amount each time, which is backed up in the equation that the nuclear radius is equal to R0 a to the power of a third. Now, it's important to note that this is actually why large nuclei need more neutrons than small nuclei, because if we keep our average nuclear separation in the nucleus the same for all nuclei, because our nuclear density is constant, this indicates that when we add more protons and neutrons to make larger nuclei, well then the radius of our nucleus has increased to be larger than the range of the strong interaction. So if we consider uranium, because our nuclear separation is constant, this means that the nucleons at either end of the nucleus are much further apart. So we need more neutrons to provide the attraction to keep them together. Whilst for helium, again because our nucleon separation is constant, this means that the nucleons at either end of this nucleus are very close together, so you don't need as many neutrons to provide an attraction to keep it together. So large isotopes, because our nucleon separation is constant, means that the nuclear radius is larger than the strong force range, so more neutrons are required to gain stability for this particular nucleus. Whilst for small isotopes, because our nucleon separation is constant, the nuclear radius will be smaller than the strong force range, so stability can be achieved in these nuclei with fewer neutrons than in the larger isotopes. So if we actually look at our equation for nuclear density, ρ equals U over 4 over 3 pi r0 cubed, we can place values into this particular equation and we get out the following. We get that our nuclear density is 3.4 times 10 to the 17 kilograms per meter cubed. So we can approximate that for every nucleus it has a nuclear density of 3 times 10 to the 17 kilograms per meter cubed. So this is actually an enormous density. If a table tennis ball was made out of nuclear matter as opposed to atomic matter, it would have about a mass of 8 million tons. Now please do remember that nuclear density is much larger than atomic density because atomic density contains lots of empty space not found in the nucleus. Again, a cubic millimetre of nuclear matter has the mass of about 340 million kilograms, which is about the same total body mass of 4 million adults. So this provides further proof, from the alpha particle scattering experiment that the atomic radius was much larger than the nuclear radius. So as the nuclear density is significantly greater than the atomic density, this suggests three important facts about the structure of the atom. Firstly, most of the atom's mass is found in the nucleus. The nucleus is much smaller compared to the atom, and an atom must contain lots of empty space. So again, if the Earth was squashed until it reached the same density as nuclear matter, it would have a radius of about 200 meters. But what stellar object in the universe will have a similar density to a nucleus? Well, a neutron star has a very similar density to the nucleus as it only contains neutrons. So this object will only have the attractive strong forces acting on it. This means that there's no space in between the nucleons, unlike atoms, so they will have a nuclear density. So whilst nuclear matter has a density of approximately 3 times 10 to the 17 kilograms per meter cubed, a neutron star has a density on order of 10 to the 16 kilograms per meter cubed. So you might ask, the first question is, why doesn't it become more dense than a nucleus if you've only got the attractive strong force acting between neutrons? Well, whilst if the neutron star consists of solely neutrons, there's no repulsive electromagnetic force present, there is a rule in quantum mechanics which states that no two neutrons can occupy the same quantum state, which we call the Fermi exclusion principle. This means that neutrons have to retain their mass and volume regardless of compression. So to do this, they produce a neutron degeneracy pressure to indicate that it won't completely squash the star to a point. But you might have noticed that actually the neutron star density is slightly less than that density of the nucleus. So why is that? Well, the reason for that is because actually, the core does have the same density as the nucleus. However, the crust of a neutron star has a much lower density, since the neutrons spread out slightly because there's no pressure above them from the neutrons to combat the neutron degeneracy pressure beneath them. So this gives you a slightly lower average density, which is why it's slightly less than 10 to the 17 kilograms per meter cubed. So if we've learned in today's lesson, we can interpret the equation as evidence for constant density of nuclear material, and we can calculate the nuclear density. So if we've been successful and learnt in today's lesson, we should be able to calculate the nuclear radius of a nucleus with a derived equation, define the nuclear density of the nucleus, and finally calculate the nuclear density. So I hope you've enjoyed today's lesson on nuclear density, which is part of the nuclear physics topic in AQA A-level physics. Thank you very much for watching and have a lovely day.